We will talk about a particular application, which is a opportunistic network based on the buses in Rio de Janeiro. That's 12,000 buses moving through 750 over 750 lines, for which we have GPS data and the identity of the buses. The idea, we want to use this network to collect data from the buses themselves, like ticket sales or occupancy levels, stuff like that. And we want to collect this data and transmit it opportunistically from all the buses to one or more collection points placed somewhere in some bus terminals. This is a very big, it's a huge network for opportunistic network research. Usually they have like 10 or 20 if you see the literature. And a special difficulty with opportunistic network is they are hard to model. Usually we model networks like a connectivity graph, and this doesn't work with opportunistic networks because the network is continuously changing. Most of the time it's like many very tiny islands which continuously form and dissolve. So we propose using a spatial temporal graph to represent the network. And the spatial temporal graph is basically a representation that captures both the connectivity and the mobility. The idea is that every agent in the network is represented by a chain of nodes, where each node represents a meeting with another node. So there are two kinds of edges that interconnects agents, representing an encounter, and the edges that represent what we call survival edges, which represent that data has been held in local buffers between encounters. It's like we unroll the scenario in a single graph, which vertical edges here represent encounters, horizontal edges represent the pass of time. A path in this graph represents a propagation history of a packet, when he was held in a buffer and when he was forwarded to another node. So a path represents the propagation, as I said. And when the first time visiting a node from an agent is the real time. So once we have this graph, we can run classic routing algorithms like backtracking or Dijkstra or distance vector to obtain the optimal path, given that we have the full graph constructed. And this graph captures the patterns that are in the mobility scenario. Close agents tend to have more frequent forwarding edges and so on. And the basic idea of the work is use this graph to train a machine learning predictor to classify transmission opportunities. Try to learn what is a good forwarding edge to traverse. So in our case, we built this graph representing 1 day of mobility scenario. It's a huge graph, but it's a relatively big graph, yeah, 20 million nodes and 40 million edges, but it's very regular. And using this basically Dijkstra, we can solve it from all nodes to all nodes in like 10 minutes on a desktop machine. And we can solve this for various metrics of interest. Now, in this work, we will present attempt to minimize the number of transmissions. So for us, the shortest path is the one that takes the less amount of transmission. This minimizes the power consumption, so to say. But we could use to minimize latency, for example.
Jorge, so I give you 1 minute and then we do questions. It's okay, 1 minute or
okay,
1.5?
Perfect.
Yeah.
Perfect. So we basically train a predictor. We try several classifiers, selecting the one that are lightweight evaluation. decision tree, logistic regression, and multi-layer perceptrons. And we obtain good performance. Basically, the best performance is obtained with multi-layer perceptron and logistic regressions. And the interesting advantage is that as the training is done completely offline, there is no routing data exchange through the network like Prophet would. For example, it has to exchange those distance vectors. So the traffic overhead in the network is relatively low. So we see that we obtain very good performance with very low data overhead in the network. And as a conclusion, we have an easy to manipulate model for opportunistic networks, which allows us to use standard tools for graphs, which can work with very big networks and can be used to model them and simulate them. And with it, we created a routing mechanism with competitive performance, which is trained completely offline, can handle very big networks, and allows to use flexible selection of features that we can train input any data of interest, like line identity, in this case, line bus identity. And that's it.
Thank you, Jorge. It's 5 a.m. in Montevideo, so
yes.
I hope you have your mate. Is there any question in the room who wants to? When your work is similar, maybe? I have some questions, but yes, you
yes.
come here so he can. We have a question from the audience. Introduce yourself.
Hi, Jorge, thank you for the presentation. I'm Carlos Gomez from the Universitat Politécnica de Catalunya. My question is that since you use the data-driven model, if you consider any model that is meant specifically for spatial temporal graphs, like for example a spatial temporal graph neural network.
No. This is the basic approach, because we are, for example, only predicting forwarding opportunities. But there is another direction that we can predict, for example, with a buffer policy, which is very important in opportunistic networks, which will consider all the edges. We're only trying to learn when to forward, but we're not trying to learn, for example, when keep data in local buffers. So our approach is very application driven. It's not very general, like a special temporal network.
Right.
But it's a direction we want to take. Yes.
Thank you very much.
Thank you, Jorge. I think it's better if we move to the other poster, and maybe in the afternoon we ask the question to Javier. So thank you very much for your presentation, and let's move on to the physical poster.
Good flight.
Good. No, Jorge it's in Uruguay. Javier it's okay. In the end. Yeah. So you can go to sleep, Jorge. Okay. Thank you very much. So I propose that we all choose one of the two posters we have here and enjoy the rest of the morning before the coffee. I don't know. I can ask. We record the poster? No. No, because remotely is not. Okay.
Because we have a few people that want to explain to us quickly.
Maybe we can do it again. If you maybe better. Yeah. So who wants to start, gentlemen?
Okay, thank you. I realize that in current monitoring approaches, each use case is tied to a physical deployment. What I propose is to use to do monitoring thanks to Massive Iot Paradigm, which implies that tiny sensor in huge amount on battery powered on LP1s are transmitting and help for monitoring. What I propose here is first a framework for new monitoring strategies thanks to this hypothesis, showing what is a monitoring strategy and then how to quantify it thanks to quality monitoring metric, which is versus energy efficiency. They are opposing. That leads us to a multi-objective problem. And after that, we propose a first instantiation, a first method for monitoring strategy, having another hypothesis, which is receiving strict periodic reception, and we show that there should be a compromise between energy efficiency and quality of what we receive through the metrics we showed.
Yes, your turn. Or maybe question, or we do the.
Oh, maybe I can be a bit like it was just a really short presentation.
Okay, let's do.
So I think, yeah. I
Let's
didn't
keep
know
the
what
flow.
you wanted me to do, but
Okay, so what this was about, so that's we are in a cloud native environment and we have many microservices, and logging is of course very important for every microservice for proper observability, monitoring and troubleshooting, and for many other reasons. But logging is always a secondary task of a microservice. So in an ideal case, logging would be very
Is the session over?
No.
Can we join?
Sure.
so in an ideal case, a logging framework would be very optimized and resource cost would be minimal. So that's what I try to do here. On the poster there are two scenarios highlighted, where I created a logging pipeline, and then I try to measure the footprint of the individual components of the logging pipeline. So that's a short summary.
Okay, thank you. Maybe I have a question for you. So when there is an event that you want to log that happens on an IoT node, maybe he doesn't have the login, right? You do at another server in the cloud. How you forward this how you forward this information? Maybe you do a buffer of the login and then you send, or because I work with IoT and you cannot sometimes you cannot allow to send immediately information. You have very limited, or maybe that's another.
There are many different logging scenarios, and well, I use the Elastic Stack here, and it can be utilized for all. I can't imagine a scenario where it couldn't be utilized. So here, for example, in this pipeline, the log generator is the IoT.
Okay, device.
Component. Yes, and when and how many logs it sends,
You don't in your model. You don't. Okay.
So, and there could be multiple methods to send the log. So HTTP is just one example, but it could be anything.
So where you specifically optimize the resource consumption at the backend, let's say, or on the whole chain?
Well, every component of the stack could be. There are many possibilities for configurations, for different configurations, and it's really hard to come up with a model for the overall optimal logging because of the many different configuration options. So that's why it's interesting.
Okay, nice. And then some question. I don't want to monopolize the.
Okay, just a quick question. I was wondering how did you measure the CPU usage?
Well, it was we were working in a Kubernetes cluster in this case, and we used its own monitoring.
Okay.
Why not use log generators in every port? And then you make the average of all these ones that give you the statistics of the performance. and you identify the posts that are not behaving correctly, and then you go into events detection rather than application detection, because applications can be corrupted. Applications, someone can hack it and just make it work. But then the volume would be on logs files. No? I mean, why to choose the cloud base rather than the application base rather than cloud base to quantify it?
That's a good question. This is a scenario we were looking at. There could be other cases, of course, and maybe regarding the footprint what we measured here, it wouldn't really make a difference. But it would be interesting to look at.
Sure, it's a helpful one. And maybe for this one,
Yeah.
you mentioned about the quality of the data, right? So
Yeah.
take the 3 monitoring strategies. But how do you assess the quality?
Oh yeah, that's a
Without
really good
having-
question. I didn't explain it that much. And like in the literature, what they are taking as quality monitoring, quality metric is like coverage area, but like knowing the position of the sensors. But like in Massive IoT, we cannot know the position, the precise position of the sensors. And so in this first work, what I suppose is every emission is atomic. Every emission that is sent from one sensor is atomic and they are completely equal for the moment. And what I propose as quality metric is diversity, which is the number of information coming from different sources, from different sensors, and I weighted them with an aging function. Like an information which is quite fresh will have a lot of importance, and an old one will have lower importance. So the diversity at one time is the sum of the information coming from different sources weighted by their aging function. So the principle is to have quite a diverse information reception in order to do a good monitoring for the following of the physical quantity I want to monitor.
If I got well, so you define the T,
Yeah.
is your PN fixed, and then based on that assessment, that's the quality of the monitoring part.
Like I used what is called the freshness function. Yeah, and like there are different kind of freshness function, but a simple one can be like during a time t, every reception is equal to 1, and if it's older than this, the information is not relevant anymore, and then it's equal to 0. And then during this period t, I try to find how many sensors emit during this period in average in order to have the average diversity. Okay, in this time, in the precedent time t, I have like 10 different sensors who emitted, then I have a diversity of 10 in order to know that.
And then you compare with time duration.
Yeah, exactly.
But then massive IoT is for the number of devices or nodes, not for the number of data that you generate.
Yeah, exactly. Like for what I suppose is like a tiny sensor with like $1 sensors, which is tiny and like really fragile, and like with low battery, and that I need to be really efficient on them. And if I have a lot of sensor coming into the environment, I need to split all the consumption between all of them quite dynamically also. But it's not really about data, right?
I mean, the data could be corrupted as well.
Yeah.
The data in its own could be not quality data. Right?
Yeah, exactly. That's one of the topic I want to work on. Like, since I have a lot of different sensors, I can know if like some sensors are emitting some local physical quantity, but I want general over average of physical quantity.
Yeah. What you can do for future is to take a sample of the data,
Yeah.
and then you go with the content or with the packet size, and then you compare the next time, offline or even online.
Oh
And
yeah.
then you will have two quality checks. The one is the time response, which you have a strategy, and the second is the content of the data with the packet size.
Yeah, yeah,
And
yeah.
you can guarantee that at least your data is not clean. Good.
And one aspect of your work, when is that you have a controller that tells the whole nodes what's the rate of emission they should do, right? To
Exactly.
maintain the same quality of to apply because it has to be a downlink message.
Exactly.
It's like a God mode. Normally, you don't even have the information of Keynote.
What?
You have ideas about that?
Yeah, exactly. Thanks. That's why I modeled a framework, a strategy for my purpose. Because I'm working on LP1, I took like, for example, LoRaWAN class A network, and I consider like a period update function that can be used every time a sensor emits. It opens a listening window, and then I can change its period emission. That's everything is like on what I'm working on. I'm just sticking to this scenario, but like it's for this special instantiation, it doesn't work very well for packet losses for LoRaWAN class F, for example. But like for further work, we are really working on like robust period update function that can really handle this problem of packet loss during the emissions, and also like, yeah.
Okay. Thank you. Any more questions in the room? We are almost 10:30. So. And we will have, I recall you that we also have the panelists, the poster panelists this afternoon at 16:10. So we will still, if you have questions, we still have a chance to ask them. When they go, so we thank you and maybe we'll have some drinks and chats.
Yeah.
Thank you all. And the session, it's at 11. We come back here and we have the grand opening.
Non sweat c'est pas local. Because I thought lost yeah, really lost.
Hello. Are we getting ready to begin shortly?
So I would show you, share just this screen.
Yes, you're allowed to share the screen, so you can share your screen on your
That's like maybe
Recording in progress.
Okay, so welcome everybody. So as we have now a lot of people, maybe we start. All smile and look to the camera. Good. Okay, so we had a fantastic start in the morning already, and one welcome also from my side. So I have about 5 minutes left as I see, which should normally suffice. So the conference, the workshop this year was organized by me, by Hannah and Lucia, by Stuart Clayman. Hannah is remotely participating in the Zoom call. Stuart will come here also later, I guess. And this year we had Filippo and Renzo, who strengthened the organizing committee, and they did a fabulous job in doing most of the work that was done for the workshop. And so thank you very much for that. Give them a warm applause, please. So they had the perfect start for getting into the conference business because they had 3 old people telling them what to do and how to work on it, and so they did a very, very good job. Thanks a lot for that. Okay, so the opening, I quickly wanted to tell you a little bit something about the history of this workshop series, because it's actually already the 5th edition. Even though it's the 2nd edition under this name, we already started back in 2018. And just this morning I added this info to the website here. And when Hannah and I started this in 2018, there was not so much IoT management in the network operation and management community, and we thought, okay, we have to change that. Because the IoT is a super important topic, a super important system that is gaining importance since then. At the same time, the network operation and management community has lots of methodologies and tools for doing structured management of anything actually, even though they're focusing on networks, and therefore the idea was really to combine the two.
And as these are hardware and software systems, so cyber-physical systems, another important aspect of this workshop series is the softwareization of the management. So how can we have distributed management systems for heterogeneous systems? So this is basically all this. And therefore also the original title was Decentralized Orchestration and Management of Distributed Heterogeneous Things, because this is what we do, but managed IoT is of course more sound, and therefore we also switched the name last year. So the workshop is traditionally co-located with this event series, so with the NOMS and the IM, and it's running continuously since 2018. Only in 2020, as I was the workshop co-chair, I didn't run the workshop because Maura and I thought, like, okay, it's better if other people do the workshops when we are organizing the workshops. Okay, good. Yeah, and so I'm very happy to see you all here. You're in the right place. It's the best spot to be at the moment, of course. So for the agenda, so Renzo was telling it already. So thanks to Mauro, we were really able to comfortably arrange the program around the time, because this time we really have all the elements in that I love to have. So we started with the posters. The poster people did a great job in presenting the posters. So this is present. The idea is also to go there in the coffee break and look at it, because originally in the dance schedule it was only time for coffee break for the posters, and that would have been really short to look at them. The madness is also something that I found very important, because it's a great way of getting an overview, who's talking about what, and getting a short teaser, what you can expect later. The keynote, of course, always one of the big highlights. So we were actually, I guess, the first workshop in 2018 of introducing keynotes. So nowadays every workshop has a keynote, so it's good that they adopted this as well. Yeah, yeah, basically, so this is all I wanted to say for this grand opening, as I was entitling it. So you know the program is on the website. Yeah, so first part we did already, and the next item on the list is the keynote by Martin. And I have the honor and pleasure to welcome Martin Serrano with us today. So thanks a lot for coming over from the UK. We're honored and looking forward to the keynote. Some words about Martin. So Martin is the head of the Internet of Things, Stream Processing and Intelligent Systems Research Unit, and scientific director in the area of Internet of Things at the Data Science Institute inside SFI Research Center for Data Analytics at the National University of Ireland in Galway. And he is an international associate scientist at the National Institute for Standards and Technology NIST, at the Smart Connected Systems Division in the Communications Technology Laboratory in Gettysburg, Maryland, USA. So he's probably traveling a lot also.
Doing talent now.
Yeah. And yeah, he's listed between the top 25 key people influencing the Internet of Things by Silicon Republic, and awarded with the NGI Explorer Best Impact Award, a prestigious award for his achievements and trajectory in science. It's equivalent to the Oscar Awards, so very good. And besides that, he has more than 15 years of research experience and had leading roles in different consortia in national and international level. And he's also very active in IEEE and ACM, and he's the author of the academic book Applied Ontology, Engineering in Cloud Services, Networks, and Management Systems. And that said, Martin, I would hand over to you for the keynote, the evolution of the Internet of Things, science perspectives from IoT device management to managing the IoT full stack at the edge, and from data collection to data marketplaces. I just stop the sharing here. Yeah, so we can also welcome Martin with a warm applause for the Look Sports.
Okay, thank you. Thank you for the nice presentation on having me here. Actually, most of the time when I go to speak in keynotes, openings, I'm used to say what exactly I am and what exactly I do, but I think this time has been done already. So what I will just go through is probably a small passage of what I have achieved rather than what I have done, and most likely to incentivize or invite everybody to do IoT, because IoT is just taking off, and you will see in these three sections. I will try to keep it very dynamic. So the first part is just to demystify the IoT, because many people think it's on the technology side, it's only sensors and electronics, but I will go beyond that. It's just a hype. I will do also an application that we have developed recently with one of the PhD students, which is working at the edge of IoT, edge devices, edge intelligence. And also we have been modeling some management methods, and was mentioned before that management has been delegate or has been delayed, but now should be taking over, because with all this amongst information that exists from IoT devices, these massive IoT devices that are connected now, we need some management techniques, management models that will be more efficient. And this is very practical, so just put it in the middle, then people can a bit awake. And in the last part, I will just go with what we call the action plan, so a roadmap. So how we can IoT evolve towards what are the next expectations in 5 years, few years to expect that. So these three sections might go around 10 to 15 in between. I don't know if this still the 45 minutes talk and then Q&A, right?
You have a bit more.
Oh,
You have.
I'm not prepared for that long, but
Let's see how it goes. It's okay.
Okay, so what is important is the simplified things. So in the beginning, I started as an electronic engineer. So my background is really pure VLSI, large-scale integration devices, it's silicon. Then I move on into this communication area. It's not really clear, sorry for that. Then I move to the communication part, so management, protocols, and see how this can be combined. But then I got the opportunity to work for a large company, Panasonic, when I dedicate my time to do some research, and I was more like touching the standards and say Sigma, 3 Sigma. Then these three dimensions gave me a very solid background on saying there is something that has to be done in terms of the internet. And then the internet was basically the main driver for me to go and excited and to move into a PhD. So it was kind of a more research in better on that. Then I got this position on as a research assistant, developing code, as everybody started probably. And then the opportunity to do more research studies and intensify this research into a PhD was back in 2008. When for the first time I was thinking on smartness in the box. So how the boxes, how the routers, the gateways will be communicating each other rather than someone coming in as an engineer and configure them manually. So what was today's called plug and play, but in that time was still not at the device level. So then how we were using semantics. So using data models that we were rich enough to start to exchange information between these devices. And then on top of that, we had the layer of ontologies. So this ontology I will demystify as well, but at the end it's just format, a data model that will go traveling and will be consistent all across the devices. Is this going to be possible in IoT? It is already. So this is something that we'll explain. So in all this kind of adventure since I got my degree, so I went to do internships in Motorola Labs, basically in Ireland, so that's why I moved to Ireland. And then I created a research unit, small research group. At that time was about connecting devices and internet, and basically cloud computing. And then I started to add layers on top of that. The data sets, the semantics, and then becomes the time of IoT boom, the hype, IoT technologies. And then I started to do more like lean data on top of these devices. We call it virtualization at that time. We just don't call it lean data in the semantic way. Then started to create applications, human-centric applications like semantic web, big data, and then on top applications like smart cities, smart manufacturing, and very verticalized. None of them were connected to each other. Still was very isolated technology. But this is the origin of the unit. Then I expanded to a more data processing, how to do more intelligence in this data analysis, and how to do more automation in terms of AI, in terms focusing on terms of the economy. So the mission that we have in our unit, in my unit, is to interconnect the physical with the virtual. And for that one, you can imagine these sensors or these actuators getting information and transform this one into a virtual representation. We call it virtual sensing. So it's a common term that we have since 2015 when we create this unit. So this virtual sensing allows to interconnect physical and virtual transparent. So what is in the middle? This cloud, what we call LOD, link open data. So all this data is accessible, is exchangeable, and can be accessed remotely or locally for any device or any application. With some restrictions, of course, with some privacy elements, but we'll combat them. We need obviously management of the data, we need cloud infrastructures, we need all these platforms for middlewares that we call today, and we also have these sensor networks as a main driver of our unit. Now, the expertise comes from management background, so believe it or not, this is my community. When I started in 2000, I was a member of this NOMS, IM. All my publications were emanating from these communities, IEEE, and later on I moved to ACM. So because in computer science we have more ACM background. So my presence is in both units or in both organizations, but this is my roots. So I'm proud that I'm coming from this community, and I'm happy to be back now after so many years on that. So now the specific focus was the full stack. So we're talking about an IoT stack, layer over layer over layer, which is not necessarily the OSI model. So the standard organizations has done these 7 layers applications, while in IoT cannot be that long. So we don't have this capacity. We have constrained devices that we see today in the posters. They are targeting to have the energy efficiency, harvesting energy. So this could not happen with the OSI model. So that's why we proposed the IoT stack back in 2015 in the IEEE journal. So you can check that publication as well. But the most important in this process is, because this is valid, how this can be validated. So since 2013 or 12, when I started to work in this European projects as a coordinator, then we created this Open IoT, which was the objective to connect all these devices via semantic layers, via this layer. First layer on the stack on top of the sensing layer. Then we went to specific virtuals, verticals, which was the smart cities with Vital, and we demonstrate that cities can connect and can talk to each other. When I said cities, I mean the systems in the city, right? Traffic management systems with energy systems, grid networks with mobility systems, etc. So all this was possible with this another layer on top of that, semantic layer and then application layer. Then what we have is also kind of federated systems. So in Fiesta, what we did was the federation of all the systems. You know, by management, in the management community, the most complicated part is who has the right to go first when there's a request for information, or who has the right to respond first when there's a request from the customer side. So Fiesta was precisely the federation of these IoT testbeds, IoT deployments, and then we managed to articulate that smart cities like Smart Santander or cities like Galway can articulate information across domain in smart cities. Then what we did is let's go expand this one in a large scale. So big IoT was in the time of big data as well. So we started to produce data sets among large amounts of data, and then we create this ecosystem of large scale pilots, preparing what's going to happen these days with among this information or a large amount of information. Then we want to apply these concepts into what we call a specific vertical like key for Europe, healthcare, right? Wearables, right? Agriculture. Then we went also to the manufacturing. So all these were 5 large-scale pilots that were funded in 2018 and run until 2021, last year. And I was one of the main editors in Activate. So we were into the health sector to demonstrate that the IoT can scale up. Obviously, this is in the context of research, but nowadays it's coming more as industrial solutions. And then suddenly it came to me the opportunity to work with some financial fintechs, you know, the cryptocurrencies and markets are taking over. And the best scenario is when you have your devices associated to your daily life, and these devices, the information that they produce can help you to get good premiums, to get good opportunities in these crypto markets, or as simple as you can be more competitive and get more better offers by banks in terms of services. So because your behavior is, let's say, your driving conditions are good, then you can do that with insurance. Because you are a very loyal payer, and you pay your loans in time, then the banks can give you a better credit score. But instead of you filling forms, instead of you going and ask, your devices will talk right for you. So your fingerprint is the device's connected. You don't have to do anything else. Of course, there is a revolution in this, because there is already regulations, GDPR, privacy issues, that we are attaching this Infinitec project, still running until the end of this year. And then the next wave is also, what is going to happen with my data? I have all this data from my device. I have my mobile phone. I have my clouds data, my images, my sensors data. And should I just give it away for free? Or now the regulation that helps me to protect that is it also allowing me to sell it? So this is the next wave on IoT, so selling the data as well. So from devices, collecting data, storing, exchanging, building applications, and selling data. So all this is an evolution of applications that we can learn today as kind of an evolution of that. And that's why I call it the evolution, the evolution of IoT. And the most important is also some cross-domain projects that I have been personally involved. These are more like small projects that touch elements from that. And here is when I got the opportunity to work with the US government and create some standards for the US government that are basically applicable for any government. But this is the collaboration that I have at the moment with the NIST as an international associate. Now, the point in here is, what is the value beyond this? So we as a research community or as our practitioners in science, how we can allocate this one. So I just want to make quite a quick review on the concept of science. So as you know, the science is applying the scientific method as a simple definition, but it goes beyond just observing and having natural elements. It's going collected formal methods, it's principles that we can create and elaborate, but most important to justify and demonstrate. So this is the part that science allows to do. And if we take memory back on the basic science, immediately people think, okay, chemistry, engineering, physics, and biology. But very few people think in computer science as a science area, but basically it has been there as applied science. So it's in the history of computer science, we have now even inclusionated this one. In the past, 20 years ago, was a subsection in engineering, but this is not anymore. So we have computer science, we have data science, right? So as well. So how this can be evolved, because the evolution of computers has come as different from computer science history. As you can see here, the first computers started in the Chinese time, analog computers, and allow me to do this kind of a passage very quickly because I think everybody has fresh. It's just important to have a refresh from time to time. But let me focus on this part. In 1821, when the magnetic computers were transported into electronic computers, is the emergence or the born time of our era, modern times of computer science. Still, we were not focused on data, we were just focusing on operations, right? And then back in 1973, when this reached the market, when these computers were less expensive and in size more, let's say, practical, is when we started to get these computers at home or more general purpose. So we have two eras that I will identify. And we always landing the computer science in between these two eras. Now, remember, it's not about computers as a hardware. It's about the capacity to have computation as part of that. Now, how long it takes to create from a technical or technology-driven approach to be a science, to be more formal methods. At least in computer science, it took around 20 years. So the ACM and the IEEE created was in 1947. But from 1937, when the first electronic computer was created, or was kind of viable, to 1958, and just an average between 51 and 73, is 20 years. So that was, and what is the reference? That the first degree in computer science was in the universities, basically. So there's a formal studies on that. There is no other way to measure in society is a science or not. Yes, we can be practitioners, we can produce our scientific papers, but if there is no degrees, if there is no formal studies, if there is no certificate behind, the society is not recognized that. And it's just a metric, KPI. Now let's see what happened with big data. First of all, machine learning, big data, and data science is different. Most of the people that I have been talking with mislead or misunderstand this part. So data science refers to all the areas, all the knowledge areas of data. Big data is principle, right? System designs, industrial engineering. So we have statistical stochastic methods. All about data science refers to progress in mining, in understanding the data, analytics, analysis, all these are the areas. While in big data, what we have is basically a small overlap between data science, which is basically mining, and this volume of the data. Big data only focuses on the volume. And as such, we can develop what we call the artificial intelligence elements, which is machine learning and deep learning. But you see, they are complementary, they are not the same. So in the other side, we have machine learning as this modern term of AI. So there are overlapping, there are connections, but they are not the same. This is the main message for today. Now, what it happens is that data science is also an interdisciplinary field that uses scientific methods and processes to understand the data. And then as such, the data can represent or explain physical elements or virtual activities, right? So virtual twins, digital representations, all these were known in this data science, but you see is the representation of all these elements. Let's do a retrospective in data science, right? So the term was coined in 1997, very recently. So after the computers were accessible for normal people, yeah, for post-consumer, for commercial. Then in 1998, the term big data was coined. So then we started talking about big data very early. And then we talk about 1999 of IoT term. So 3 years in sequence, right? So it was coincidence or not, but this is what we call the generation of the evolution, right? When we talk about data science, big data, and IoT. Nevertheless, the IoT was not very active until 2015. So that was the natural wave of that. But if we see the data science, it started in 2002 until 2018, so it's around, again, 20 years, almost 20 years on getting a degree. So then the first degree on data science was in 2018, with these universities having data science as a degree, a certificate. So essentially, it is the born of this data science times. Is the IoT suffering the same effect? It's some of the questions that we might need to stay to answer as a scientific community. Is the IoT going to take 20 years to do the same exam? We're not in those times when the internet was restricted. We're not anymore in these times when the communication was limited. Now we're in the opposite. Fast communication, data accessibility. You don't need to even do a degree in person. You can do it remotely, online. So essentially, the IoT is going to should be taking less than that in theory. Right? Let's see what's really happening. So the network started to be host to host. You remember this model of the internet. Then we started to do the web host. These terminals, the green screens, the amber screens just connected to the remote server for basic services, basically internet, basically email or messages. And then it goes to be integrated in the mobile devices. Remember this Nokia phones when you were texting and then the mobile media content. And now it's everything. Now we have not only mobile but also have people, also have our devices. And then now we have this internet of everything, right? Everything connected. The car, the house, the devices. So essentially what we are talking about is a new era of everything connected. And in 2019, the first degree in IoT was announced by the university in the US. So less than 20 years, but more or less the pattern is repeated. So are we now talking, or shall we start to talk now about Internet of Things science? Are we doing science? Or are we just applying techniques to improve the approach? So this is what you can maybe argument, we can argument the rest of the day, but my proposition is let's talk about IoT science. Why? Because IoT science is well fundamented. There are many areas, and the main element for IoT science is precisely the data, the platforms, the devices, and all the elements that we have learn and practice. And even one more element is managing of all these IoT devices and managing of the data. And it was mentioned by before, so we were very early in 2018 proposing that one as a community, but now we're taking the challenge to do IoT science by proposing this area, or these areas. Okay? So, back in 2015, the first release of the IoT stack didn't drive the data-centric approach. So we're just talking about devices basically, protocols, the machine-to-machine end-to-end protocols, and then we were just talking about atomic applications that can use this data for analytics, for visualization. It was nice to see a graph of data and then some applications. But this has evolved very fast. Now we have mobile apps that collect your data, see your vital signs, see your behavior, your traceability. Most of the applications today rely on sensors, relies on all these Bolt or all these Ubers, so are basically from sensors, right? So this is the day-to-day, right? So that's why we are now updating the IT stack and making it data-centric. So the data-centric approach is we have raw data from sensors in the bottom layer. We have a methods to collect and model that raw data. Still nothing to do with semantics, it's just raw data model. We can talk about JSON format as an example. And then we have these data platforms that transform and use a more elaborate syntax. And here we can talk about XML, maybe HTML, maybe JSON LD as a format that we can manipulate in that one. And then we have this more like an automation based on schemas. So when standards become to be more useful in that. And then we have this knowledge platform like a metadata graphs, and it's very common now to have graphs in the applications. And then we have the business process as analytics. And I make an analogy in this new IoT version of the stack in some kind of a drops in the left. So raw data is this unconnected information from your sensors, temperature, humidity. And then when you start to do more kind of a connection in between, you have this edge server device. Yeah? This data becomes to be more kind of a drops in a rain. You see a cloud and the rain comes down. Then the edge becomes to be fog. Right? When the water evaporates and everything to be all connected, it's very misty. It's what we call the edge processing because it's everywhere, basically. But then you need to establish the connections in between. And the sustain on this one is fog computing that already has been developed. Cloud is well known and no need for explanations. When all this data is already connected and mapped, then we have these cloud-based systems for supporting IoT. And then we have this web cloud system as well. Web cloud with all these semantic web technologies, web WC standards. And then we have this web of things. So all these are initiatives that I not invented, I didn't invent it, so I was just following the evolution of this one. And then we have all these 6 levels on the IoT stack. Before we were 5, now we have 6. But this at the end is not enough to be surprised because it's just a natural way of these IoT connections. Back in 2016, we have this SOFT, which is the paper that we publicized, we published. It explains basically the IoT stack from a sensor perspective and fog computing. And now we are proposing this evolution on the IoT in science, IoT science at the edge. So the missing link between fog and raw data is edge. So processing everything in the edge. And hopefully this paper will be also accessible for you and will be publicized in the proceedings of this workshop. So the idea is to have some enhanced management methods. So we need to talk about federated models, we need to talk about self-sovereign models, and we need to talk about the maximum, which is autonomous models. So let me take a few seconds on each of them. So in the beginning we have the federation. So you need to have sensor networks that are interacting, and each sensor network will have their own way of resolving problems, collecting data, sharing the data. But by federation you will have a central entity, a manager, what we call it, and then we have a registry of events or activities on the right side of the image. Then every manager, when you come from different nodes, will register in the registry what activities or what priorities they have. And here you can come with policy-based management systems, rules-based systems to control that registry. Or modern times by using ledgers as well. So, but let's come back on this one. But the basics on this federation is that you need to register with your activities, and then the manager, which is the first one, will be the one that controls who is happy. This is the federator at some point. And let me just welcome our colleague Stuart. Welcome to the session.
Thank you.
And then the second model is basically self-sovereign. So if we replicate the same schema, but now the managers of each sensor network is able to decide and define by themselves what are the main priorities instead of the registry, in this kind of a self-sovereign. They define or they decide by themselves. Still, they have to register what is the definition of that. But it's more like reporting rather than consulting. And you see this part in the bottom, especially the add, the modify, and the select of operations. In the previous model in Federation, none of them has this capability, right? But in the second one, they have the capability, and the self loop is to confirm that they are able to do the self-registration. Now, in the more, let's say, advanced models, what we will have is that this autonomous will have the capacity to each of them register, act, modify. So it becomes to be like a sharing federation, but at the same time self-defining model that they can exchange and they can write. What is going to be different is that the registry will only keep the record, and all the instances of the managers will back up that record. Now you start to think about maybe blockchains as a possibility, but blockchain will be only the implementation part. We have a distributed ledger, can be another part. So all these are just tools that will facilitate this model, but at the end, this is what will drive the possibility to have multiple and massive IoT deployments, to manipulate, to manage, and to control. So those are just management techniques that we need to explore. In this paper, that I mentioned before, so we're explaining details. So the idea is for today just give you the flavor that there is possibilities to do, and there is a future to go in that direction. Now, let's get back for a second to what we call about applications. So when we talk about edge devices, edge intelligence, today is very common to talk about these edge devices. Together with a PhD student and some other collaborators in Google, so what we have done is first implementation on AI at a device level. So instead of using cloud deployment, we use device level. So the idea in this was presented in Fosdem in February this year, was well received. Of course, it's a prototype, and of course there are many things to do, but the scenario is basically to collect data from multiple sources, to associate this data by having local information rather than the cloud, enrich these devices or this information with a loop, a self-management loop, and then evaluate the capacity to take decisions at the edge, at the device level. And obviously we will have a response of that decision. Now, starting with machine learning, so as basic element and electronics, because this device needs to be connected. We also need to know what exactly is happening, and we call it knowing what you don't know. Yeah, it's kind of the Siri version, but in an edge device. So you ask Siri, and then Siri responds to you. You ask Google, and then Google responds. Right? And you ask this device, edge device, the edge device will reply to you. Now, the scenario is a car, a simple scenario where we produce data from the different sensors in the car. You might know that the simplest car today has more than 350 sensor systems. Between parking, ABS, braking, 350 patents just for a sensor network. So imagine the number of sensors that you have, around 3,000, 4,000 sensors. So all this is reflecting data, right, that we can use at the edge. We don't have to send it to the cloud. The problem is how we can process that efficiently. And then, thanks to the TinyML Foundation, so now we have the first, let's say, TinyML machine learning in the device there. So we can process it. We also are using TensorFlow. You might be familiar with that. But we are using the TensorFlow Lite, which is basically the collaboration that we are doing with Google. So now, we're also using the Edge Impulse, which is basically a visualization tool. But the scenario is just a kind of a simplicity. So we put the microphone of your phone or our device to listen what the noises in the car, in the cabin, outside the cabin, and just by training the TinyML, we can associate, and we need to train basically by providing samples of noises, what could be the problem in the car. Many of the sensors are registered by codes with your OBD system, but maybe you're curious and you plug in this into your car, some codes are useless. I mean, it tells you just reference about the sensor, the bulbs, but really doesn't say anything of the problem. Sometimes the codes are just reflecting maintenance rather than repairs. And all these things can be very costly, not only for the maintenance of the car, but also for the workshops, because the parts are very expensive. So we came with this idea of why not we train this TinyML via machine learning, TensorFlow, Lite, and we kind of put some element that give us the experience of a mechanic. And we call it whispering, because nobody will want to say exactly what's going to happen with the car, but you might not know, and then you go and talk with the mechanic. So it's kind of like someone's telling you behind the ear. And then that's why we recorded all this one on 20. So the architecture is quite simple. So we have car noise that is there. It's not difficult to find a car with problems. Then we have kind of at some time we collect this data specific period of times that I was interested in that paper. So we record the times during the morning, during the afternoon, during the evening. And we discovered that the noises in the morning are less prone to errors. But in the afternoon, after the heat of the car, after the use of the car, the errors becomes to be more evident in terms of noises. Right? So that's why it was very interesting to have these time slots and classifications. There were also noise data that we can consider peaks or events, and we ignore those. So still the tool needs to be trained more, but you will see the results of this. Then what we added on top of that one was a metadata, so a description of events, a description of errors, that we already know what's going to happen. So there are some noises that are very characteristics in the cars. Valve noises like clack, 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 or maybe some pistons that are misfiring. Maybe you're running the car what we call rich in oil or rich in petrol. And we don't have yet odor sensors, but it's only with noise. But then we can have this one as a recorded audio. Then instead of processing the live sound, we process the audio. And as you know, in machine learning, in AI, the most common method is using audio files, right? Image processing. So that's why we have CNN, convolutive neural networks. So that's the kind of the method to. Is this possible to do it at the edge? This is the main question. The answer is yes. So in this demonstration, Owen did it very well, but he was looking at the considerations. The option one, go cloud-based, as everybody might do it, but let's do it in our own architecture with an EML, and then let's do with this IoT measuring, data modeling, then with data insights, and then IoT. We implement basically the central part, the intelligent edge engine. The rest is just the IoT part and the IoT application. Sorry. So why in IoT, or why at the edge? Because it's inexpensive. Owen bought it by $20 or 20 euros, less than 20 euros. It uses Arduino as a prototype and some sensors from Seed. So very simple, very high quality device. And then obviously we don't need to have connection all the time, which is the most complicated part when you are in the middle of the roads and there is no good signage or good coverage. And what were the main challenges? Well, to be kind of a well-known and pioneer this example, has to be an open architecture, and that everybody can get access to it. Performance, look at the performance and make a good analysis of the data. We need to use wireless networking because you cannot just go and connect your cables in your car. It has to be very resource efficiency and energy efficiency to don't run on the battery car, but run on batteries. And then have some security and privacy concerns. So we don't want to share this data. Basically because maybe insurance companies can take advantage of that. If they know that your car is not well maintained, they will not offer you good premiums. So we want to keep it at the edge, protected, secure, at the same time, I want to use it maybe in different cars for my house. So that's why it needs to be cross-platform and federated. Now, what was the result of this one? We need to explore TinyML. So indeed, so that's actually what Owen is doing in his PhD, developing something with TinyML. Also, we were looking at the hardware itself, because this is a mixture between hardware and software. As I said, this is just basically an Arduino. There's a new version that has the SP32, which is very, very efficient. And it also uses the SPI, which is basically the latest development in Arduino. It's not expensive, but I said around 20 bucks. And then we will attach in more devices. In total cost was 120 euros. But we attach display, we attach some sensors, we attach the, and of course the software file. And we started to use the audio set, so we need to train the machine, the AI, and then using JamNet and audio sets that we were found in different networks about the noise of the car. He was also recording his own car noises to know exactly what happened, because he knows more than anybody else what's happening with the car. And all this one was related to air leaks, flywheel problems, maybe the bushings, the bearings that are born, the shocks, sometimes the noise on the roads, the brake disc, all these noises that we already know, were pushed into this training model with audio files, and then we were able to identify those. The idea is to have this kind of injected in the TensorFlow, and as you know, it's a large data set or large database, but now in the light micro version, that is kind of a zip version of all these files. Now, we were capturing data at the beginning with a display, analog display, and we were able to identify some patterns that were not easy to detect. So it was kind of making an exploration and find something that you didn't expect. So all the models that we were injecting, and something comes new. Then, because in a display we cannot see anything, so we upgrade this one to a mobile app to see how this can be work. So to essentially see what's happening there. And then this is just an example of how we inject the model, how we train the neural network, and then the outcome of this one is here. So here this is the application, H-Impulse. This is also a viable open source. And in here you can inject all these data sets and just get some consistency on that. Let's see how it works. So this is on the right hand side you see the display, right? As I mentioned, I have two videos, one with the display and one with the application. In the display we just see numbers, codes, that doesn't say anything. But in this one it's interesting because we code this one with the data model, and then we put some messages. So you will see in the video, I will explain before because I cannot speak when I'm sharing the audio, otherwise will be feedback with on. In the first part you will see that we identify when the cap is removed, there is a characteristic noise, but from the inside, from the cabin. So see this type, nobody will remove the cap, but if something goes wrong into your engine, if the what we call the gaskets are worn, this is going to be the noise. It's like we're removing the cap. There are other noises that happen in the engine that are reflected in the cabin, and just by understanding the noises, you can get alarms or sense signs. This will not be reflected in the OBD. Never ever will be detected, like say, telling you what's happening outside. It's just if the sensor gets damaged, but there's no sensor. In the second part, you will see from the outside as well. So, today in mechanics is very typical. They go and they connect the OBD, and they put the codes, and they tell you the status, and the mechanics can proceed with fixes. Well, the idea here is that nobody will touch the car just by listening to the noises, and because the tiny ML is already working to understand the noises, you will see what's happening. So this is the second part of the video. Let's see this video. I'm sorry I had to share again because I need to unblock the audio. these columns, there are already errors that we know, like leaks, air leaks, bugs. These are the models that we train people. But when it says uncertain, it's because it's not kind of comparing. There's a new noise that we are not able to identify. Or as soon as it goes, it's a problem. Right? Okay. So you might wonder, is not the processing and device the mobile phone? No. We're using the app to visualize what is happening in that small device. So everything is running in Arduino with the TinyML, and then we're just connecting to via Bluetooth to visualize this application. The mobile phone is not processing anything. And as I mentioned before, if we remove the mobile phone, we just have this display with code. So what we encounter is that we need to do more analysis on that. We'll proceed or we'll continue with this one. But we have some kind of a premature conclusions. It works. I mean, AI-enabled devices can run at the device level, right? We're not talking about powerful devices. We're talking about Arduino-based. We have demonstrated the low barrier between TinyML, that it can be processed on a neural network already at the device level. So we also have some kind of edge intelligence because we are analyzing in real time or close to real time. We're using the cloud, so we don't have to have permanent connectivity to the internet. And we also have some sort of a feedback back to the user. So now think the possibility of this. Think in a health device that is attached to your heart, attached to your vital signs, and you don't want to share this one with anybody else. So I think this is one of the major applications that we are targeting. Before you even go to the doctors, before you even go to the insurance companies. Because if you are healthy, you are happy to share that because then you will get premiums. But if you are for some reason unhealthy, you don't want to share this data. So even you probably might be compromised. So all these things are possibilities that we will continue exploring. But this was just a demonstration for putting the technology in place. We were not going to replace the display because the display doesn't help at all. It just was a digital, and now we are going to use a matrix display that maybe will be a better sign-ups or better representation of that. So we will look for error codes from OBD and we will combine them, because at the moment we just kept away from OBD codes, but then if we put the OBD codes as a source of information, then we will have more response. We don't want to fix the gap. We want to identify problems that are evident that the human ear cannot detect, right? And then we will have also to extend also as well with other sets that are more ontology based, because at the moment has been only a data set that we have labeled manually. But if we go and find an ontology that is for cars, then we can do that no problem. Okay, so we're getting to the opportunities, and we are also trying to use this one in ATMs, in Infinitech project. So if you put these devices, maybe someone aiming to treat you or stealing your money when you are in the ATM, or maybe the ATM is making noises, strange noises that are not common because someone already hacked it, someone already altered it. So these devices can alert the system, right? So we're detecting non-intrusive elements via this edge process, right? This is just a possibility that we're exploring in this project. And also we have the other part, which is basically how to start to sell this data. Because all these devices connected to your car, this could be information very useful for car manufacturers. So it can be very useful for companies that do maintenance, mechanics. So instead of just give it away, you can maybe sell it. So in the IT market, we're exploring these marketplaces for data from IoT devices, and we're exposing this model for further development. So it's an open source project that we are pushing towards the community as well. So all these are the possibilities in these applications, and it's just to demonstrate that TinyML and machine learning AI can be run at the edge of the devices. So edge technology is here, edge intelligence is possible, so we need to explore more in terms of capabilities. Now, the last part of my presentation, I'm still in time, yeah.
Yes, yes.
So will be the action plan. So what are all the possibilities that we can do as a community for research? As you know, and you have seen, I also move my activities around advising the community, advising the European Commission, the US government to what would be the best way to approach these challenges. And as an advisor or as a, let's say, a associate, so we need to identify what are the problems, the challenges, and instead of saying this should be or not resolved, we just put everything as a challenge. And IoT started, and apologies for the director, it was not helping, but in here is what I call the roadmap of the IoT. So we started from modeling the five layers stack with all these protocols from networks. In the central part, which is visible, you can see the ISO from these wireless protocols, from this co-op interface for connecting machine to machine to applications. So we have this UDP as security. All these parts probably well known by communications communities, but what is not well known probably and not very useful is the W3C. But the combination of all this stack is what gives us especially the advantage of processing it. It's more overlays, yes. It requires more resources, computational resources, yes. But again, the technology is not limited anymore. So we can now rely on all these applications. And it goes from left to right because it's evolving, but it also goes from, it can be read from bottom to top because it's how the IoT was machine to machine, device to device, platform to platform, application to application. So it's what we are at now. And then business to business with these data marketplaces. It also summarizes and fits well with this version of the IoT Stack 2022 that hopefully will be accessible as well for all of you. If not just one, check the IoT Stack 2015, the IoT, the IoT subgroup, and you will see the publications. You can see all the details. And I will be here today and part of tomorrow as well to discuss this one. This is more like the diagram of how you can take out or take off your IoT experience. We're coming from these protocols, everybody knows these protocols. Everybody knows Java, how to program. Everybody knows about these OGC standards, then OWL and W3C. You can go into this roadmap if you're a beginner in IoT, but if you're the expert, you already know what I'm talking about. And there's some standards behind that. It's not that it's just invented by practitioners. It's really back up on standards. M2M, HC, IQ, and we also have the RFID, IPF, and the O2C forum. Now, so IoT is not only connecting devices, it's also data-driven approach. And as such, I have this, what I call data continuum. So it reflects when you collect data as a raw data, sorry, it's a mistake, it's raw data. This is disassociated, sensors connected, imagine the sensors just connected. And then you have your data sets. Then you start to create these links or these associations. And you start to process data series, when you associate time series. And this is the most common term in IoT, time series data. But then when you go into more kind of a large data set with more data model on top, then you have these data streams. Processing data streams is the complexity of the data in your high exploration. But if you're capable to do data stream processing, what Twitter does, what Facebook does, then we have a powerful tool. And this is basically the basics of AI. When you are able to understand, analyze, and do analytics. And that's why we have at the very top of the continuum these data torrents. So when you have among those information, pieces of information, you can get value out of that by just having applications that understands. So this is the data continuum that we are also explaining in this publication for this workshop. And it takes years. I mean, it takes years of moving from here to there as a practitioner. But if you're coming from computer science, you're coming from another way. You are used to process the data, and you need to go to the sensor level. But this is the continuum of what we are proposing, or we're explaining basically. Now, what are the scientific challenges we have? If you see the surface of this iceberg, so we have the machine to machine, as it was in 2015. Let's connect devices using machine to machine protocol. Then we went to this device to device communication. Right? So platforms that are IoT driven, and then we have some sort of frameworks today that is called end-to-end solutions, basically products or market. This represents just the evolution of the solution, but behind that, or below that, sorry, so we have these elements: intelligence, knowledge production, reasoning and inference, which are areas that we can investigate more, analytics and visualization, data transformation and processing, databases and information management, and here's where we are in managed IoT, applications and services, languages and formalisms, modelings and taxonomies. All this might sound like a is there anyone from China? Like a Chinese language because of the difficulty, but at some point we should be able to process it. So that's the magic of having these research challenges. We also have to do more modeling using formal ontologies or formalisms. We have to use more research in databases and information management to make it more efficient. There's some progress already in SQL, Sparkle, that allows you to do multiple queries and use machine learning algorithms for query optimization. There's some papers that we have already published in that area as well, so we are kind of focused on this one. So we have data transformation and data processing. So all these are kind of challenges that I'm just exposing for you to, if you're interested, as starting points for continued research. Supporting obviously IT science. The idea here is not just to go technical, but also do scientific contributions. At the level of applications and services, we have FOC, we have data federation, we have semantic web models and link data for IoT. So we have some IoT stack. As you see today, we're releasing, or I am presenting the new version, but we also have the SEC 3.0, which is a methodology for federation. It's another management technique that was published for IoT in 2016. We have the data interplay, which is part of the soft paper. We use this data interplay as a means of exchanging data between different domains, different layers. Those are just scientific principles. None of them are techniques or methods. They are just scientific principles that have been elaborated and deployed in these papers. And then we have now the data management and data processing. So this is the main challenge that probably brings us into this managed IoT, because the management has been delegated, has been delayed, because it was too early in 2018, or maybe it was not interested in 2018, but now with all these sensor networks, with all these IoT platforms and devices, so we need to have proper management techniques for that. Graph-based, spatial temporal based, whatever is the techniques has to be elaborated. Before I go to the conclusion, so this is just a kind of a roadmap that you can, hopefully after today you will map everything in your head and see, okay, what Martin was talking about is this from 2010 to 2030, and see how you will fit in there. Because we as a scientific community need to fit at some point in there. If I am doing IoT systems, IoT platforms or frameworks, if I am doing Internet of Things or Internet of Everything, if I am doing Edge, if I am doing cloud, etc. So you can see in this summary where exactly we are moving on. And from stream processing to semantic data analysis to machine learning and deep AI, so we really can see how this is converging in terms of IoT. And then obviously there will be some infrastructures or technology supporting that. Cloud processing in 2015 with the IoT, edge processing now from 2025, 23, and then edge processing will reinforce HPC processing, high performance computing and stuff. So this is kind of a visionary perspective, and I might be wrong, that's correct. It's things to do in blockchain, but not from the perspective of crypto, not from the perspective of distributed ledgers. And remember, in the registries that I mentioned on the data management models, there's a registry there. So the registry means this distributed ledger that you can use for. And it's not only used for the data, it's also for security, it's also for encryption of the data. So that's why I still believe that IoTDB should be expanded more for this blockchain perspective. We're also doing some papers on that, so I can tell you this is moving well. So one of my PhDs is going to defend the thesis hopefully in May, which is basically on all these principles. It has an excellent work on that. Now, the point is, are we going to support this stack or these areas? I think yes. I mean, there are different initiatives, solid initiatives from ETSI, 1M, IERC, the IoT Council, the WTC, and the industry. So there's no other players out of this stack. So I think that's the way to go, basically. That's it from my side. I guess it's just a few slides. This is my team at the moment. No, it's not big. I encountered that if I go more than 12 people, it's very complicated because I used to focus on getting funding. But if I had 10 to 12 people, it's impossible for me to work on some papers and do these things that I like in science. So I really bid on IoT science, not maybe next year, not maybe in 5 years, but at some point we'll see IoT science more as a data science area, right? So, and I think you will be part of that if you are buying this idea. So it's all from my side. I'm here to answer some questions for 1 year, 2 years. I'm not asking you to live in Ireland forever, but I'm fine with you also. So, researchers. Thank you very much.
Perfect. So I don't know if you're aware of it, but we are both really working, or we are working in very same areas also with this data-centric approach. And I would have a quite fundamental question, which is also product. So in the end, algorithms is always about data processing, input, processing, output. And the key is always data. Because it's like the data that is coming in, I mean, it might come from hardware or from software. And it was always like that. So what is novel now in this Internet of Things? Or to put the questions in another way, it will also say, okay, you can use any distributed system and use that management approach. So what is specific to the Internet of Things?
Yeah, thanks for that one, because it's one of the challenge questions always, like why IoT is different and what is going to be revolutioning our lives. My short answer to that, which is not the only answer I have, but is an extension to our lives. So when we were talking about data, when you go to the medical, to the doctors, as an example, you have your medical records in a paper or in a digital form. And it's your data was there again. But now when you have your devices as an extension of your life, instead of relying on those documents, on the data, you're relying on the device to tell you what exactly is happening with you in more real time. Because your symptoms are not going to be the same one as 1 year ago or 6 months ago. And even better, the processing of the data doesn't rely anymore, as we see today, in the cloud or in the records. It's going to be also in the extension of the device. And then you can decide if this data is going to be useful for you, or for the medical doctor, or for anybody, right? So I think the IoT advantage is that it's an extension of your life today. Another example, typically in social media, right? So many people know each other by social media, get married, and get each other. And it's just because you go and read profiles. But will not be better if your devices, based on your activities, based on the places that you visit, match other people that do similar things? Not necessarily in your neighborhood, could be in other parts of the world. Then instead of you looking and passing the yes, no, yes, no, yes, no, or even make a program to do it for you, then the devices are interacting. So basically, the devices are doing the social aspect of it. It's too dangerous. Is it it's going to be problematic? It's happening already, but not with the devices. Someone is, Facebook is doing that for you. LinkedIn is doing that for you in a professional way. So it's not dangerous. It's just you need to take the last decision. But I think this is the advantage of IoT now. Now, what scientific challenges bring this? Protocols, analysis, synthesis, quality data. That is not. It's possible to do in the database element, but without this enrichment, it's not going to be happening. I'm not saying this is complementary, as I said in the beginning. This big data, AI, and are complementary.
Okay, thank you very much for the response. And I also fully agree with you that this ubiquity of the devices and also the cyber-physical aspect. So these will also have people on cyber dimensions, so that it's really, you cannot escape from it.
Correct.
Do we have questions? I can.
My question was, how was the process of collecting the training data for the damaged car sounds?
Yeah.
So, like, was that challenging? And how did you label them? Okay, this is the damage for this sound, this is the damage for this sound, and how many different cars and motors you basically collected?
Yeah, we focus on BMWs because it's the best documented, let's say, data sets that exist. Owen and myself, we are beamers by religion, so we have our cars. And we were always passionate on this, like, oh, we were sharing experience. It will not be good if we can not a mechanic, but someone telling us what to do, just by hearing. But then we were looking for these data sets, they are viable data sets on online, basically, on the BMW website. But also we were training the data model with our own experience. Because when you are driving, you know what sounds in your car back. That was the first approach. Instead of going to kind of official sources, we went to the offline sources. We also record our own cars, so before to create our own data sets on well-known problems. Because BMWs are very well known that they fail. They are in the road, so they are nice, they looks good, but they also fail a lot. So it was a self-created data sets. They are viable because we put it in a public repository and they are already there. No, they're not large, but they're symbolic.
Did you also, sorry.
If it's related, that's because
Yeah,
mine
was related to the previous question. So did you also train the model using TinyML, or did you train the model somewhere else?
No, with TinyML. Everything was done on the TinyML.
Both the training and the actual real-time code connection.
Everything is there. Remember, it has to be run in the device that was the first request in this age intelligence. So everything was trained there.
Thank you, Martin. Maybe quick question, great talk. So we see there is, we go higher in level of abstraction to add value to the IoT, so you go to information. But IoT at the beginning is about hardware, cheap devices, and you also work a long time with the hardware level. So how you see the evolution of hardware, because we know we are reaching the plateau where the Moore law is no longer, so how will the what do you think about hardware? How will it will accompany this evolution at information level at the edge? Have we reached a possible limit for the hardware and now we have to focus more at information level, or will the hardware still accompany, of course with blockchain, all that, I know to assure authenticity, all this, we can have maybe some hardware specific. What do you think about hardware and the relationship?
Yes. No, thanks for that, Renzo. Definitely is a continuous evolution as well. So we are not reaching even the age of the limit for these devices. So Intel has already released the first microprocessor with IoT in it. They make a big jump because they stopped that one back in 2018 to do the AI. So that's why all these mobile phones has AI. But essentially AI or IoT power is a subset of AI. So that's why, because it's data centric. So I don't see a limit in terms of stopping the development of IoT just because now they are AI centric. Because now they're focusing on this data processing. And the device that I mentioned about the Arduino is 63, the version 63, because it's now IoT AI enabled. So that's why there is no.
Okay,
the same board.
Okay, they optimize this other
They
okay,
optimize one for
that's
special chips. Yeah. Sorry, that was.
Yeah. When I look for the last one, but really quick.
Okay, thank you very much for this presentation. It was really interesting. I have also one question about the use case you mentioned. What is the objective of your ML program to be as generic as possible, or is it specified for each class of cars? Because I really think that cars are really different one from others for motor and engine and sound.
Yes.
So I don't know if it's possible to have a really generic machine learning method for this.
Yeah, that's actually a good question. To be frank, I don't have an answer for that because
And
we were just experimenting the sound recording because we knew sound can be transported into a signal. But probably a visionary perspective is to have for each brand or each car because there are common noises, true.
yeah.
But there are some specifics that we saw today, that there are some unrecognized noises that maybe are specific for each car. So,
Great.
Small question.
Really left.
So, quick one. Nomenclature naming. I noticed you used the term edge to mean a little device that was doing processing. Lots of people mean edge to be some tiny data center, the edge of the telecom domain before the wireless. Do you have any opinion on which is which or why or what?
Yeah, no, I explained in the data continuum that H from the technology side is this high powerful devices or microchips, while in the other side is more like the capacity to process data without sharing this data in the cloud. So maybe this is a good question because it can help me to clarify that it's not all about data, it's not about devices, it's a combination of all of them, and that's why we have in one side the evolution from edge devices to more high performance devices. From the other side we have from raw data to more like big data sets at the device level. But it's not about let's constrain devices anymore. It's about capabilities and capacities to process the data in this age, and this constrained device.
So you consider the edge quite a large spectrum of stuff,
Yes,
from
large.
obviously local devices all the way up to what might be, what other people consider the edge, the micro data centers.
Correct, yeah. It showed me the dots because it was a missing link, because we jumped from sensor networks, connectivity, to cloud.
Yeah.
Because it was natural evolution, right?
Yeah.
But now when we went to the cloud, we encountered these privacy security issues that we need to cover this gap by putting it at edge. And that is kind of our just content. Now, which applications are best to perform in cloud? You decide. Which applications are better in the edge? Like sample. So.
Okay.
Thank you.
Perfect. So thanks again. And as Martin was mentioning, cybersecurity of this entire stuff is super important. And as I'm heading a chair for cybersecurity, I'm also organizing tomorrow at 1 p.m. a panel on cybersecurity where we'll also follow such discussions here. Plus on Wednesday, exactly in this room, we'll also have a talk of a speaker series that I'm organizing in the Madness. And who's running that?
You, but I can run it. Basically,
we can also run it together. So,
yeah. We can follow the order of in the agenda. So I invite all the presenters from today to come and maybe align one after the other. From left to right, following the, I'm gonna show the agenda. And there is
recording stopped.
Okay.
So you have to
Gergo, when, or maybe we do inverse, and it's the same. Gergo, when, and then we have Roch, Erkin, Filippo, Arnold, and Christian. So all the presenters from today, please align, and we will follow the order of today's presentation.
The idea is that now you get an impression of what they will present later or what they already presented in the posters, and so then you have a good overview, and you can already, the reason why we also put it now is you can already discuss with people on that topic, because you know already a little bit about it.
Yeah, to be honest, the order doesn't matter as long as you're aligned, and then there is an order, great. From left to right, maybe then. You have 90 seconds, right? I'm losing control remotely. Elad wants to join. Yeah, sorry, Elad, we forgot about that. How we can do that?
Well, you can do it while I missed already.
So this
starting.
Okay, so my talk, can you maybe show the agenda? You need this or?
Yeah, I need to talk with Elad.
Okay.
I'll make it just smaller on this side.
Well, you need the title of your...
Yeah, I just wanted to point out my slot after the lunch. So the resource trade-off for TLS, secured MQTT-based IoT management. My name is Erkin. I'm from Munich, Technical University of Munich. I do my PhD there. So my talk will be about the MQTT protocol. MQTT is secured with TLS, which is quite expensive, costly for IoT devices. And what I will present is, so we try to understand, okay, how the TLS configuration affects the resource consumption. Resource, namely CPU cycles, memory, and network bandwidth. These are mostly that consumes battery. So we want to understand how we can configure TLS Cypher Suites configurations. We switch from one Cypher Suite to another Cypher Suite, and how this will influence the resource consumption. Let me open maybe 10 seconds more about the Cypher Suites, which is a combination of different algorithms. So each Cypher Suite composed of different algorithms for key exchange, for authentication, for bulk encryption. So in each category, we look for INR recommendations. I only recommend we create a short list based on these recommendations, and then we make comparisons on them. It is experiment-based, not a simulation, so we run on real hardwares, get the measurements, and then compare. And at the end, give the recommendations.
Good.
Okay, my name is Christian. I have, it's over, I guess the last talk. Yeah, so today I'm going to present the continuous microservice replacement in the IoT. I also found a bit of my topic in the Keynote, in your Keynote, which was very great by the way. And the idea there is to use unused resources, or for example, if you have like devices like Raspberry Pis, for example, they offer lots of resources today which are not entirely used by the core functionality. And the idea there is to use free resources to place other IoT services and to use these devices more efficiently. And there we will have a look at placement algorithms also from other domains, and we will adopt a placement algorithm for the use within the IoT. And I'm going to show you how we were able to improve the existing...
Recording in progress.
Okay, great. How we were able to improve the placement strategy suited to the IoT.
Good. Thank you.
Hi everyone, I'm Filippo, and today I'm going to present the paper Water 4.0, enabling smart water and environmental data metering. So in this paper we are going to propose, we're going to discuss an architecture, a framework actually, that we use to collect different kinds of IoT data, from metering data consumption to also pressure data of the water distribution network, and how we collect those data, and also how we propose to process those data on the cloud. So basically we are going to present the overall architecture that we use to enable smart metering of different kinds of IoT data. So mainly related to water consumption and also to water distribution.
Good.
My name is Untitled Chapter, and that is my poster. So the title of our work is Optimizing Performance and Resource Consumption of Cloud Native Logging Application Stacks. And the concept of this is basically when we are having multiple microservices in the cloud, logging is never the primary task of the individual microservices. So ideally, the logging itself is well optimized and has minimal resource cost. The dream would be to create a model for the optimization. During the work, we were building up different logging pipelines and measuring their resource cost requirements.
Thank you. My name is Arnaud Mogué. I come from IMT Alternative France.
Can you speak a little bit louder?
Okay, my name is Arnaud Mogué. I come from IMT Alternative France. Last year, IoT analytics show that we have 12.3 billion IoT devices. The problem now is it's very difficult for this IoT device to leave its operator in another. You propose, you will present in this conference a new method to help their end device to live in IoT device, IoT operator in another. Thank you.
Hello everyone, I'm Gwen. I also did the presentation this morning and the poster just here. I will do the other one at the end of the afternoon. My topic is, my first question was, when we do monitoring, when we want to follow physical quantity, for the moment, each use case is tied to physical deployment, which is hard because like it's not adaptable over time. It's really strict and really rigid. And by contrast, what we propose is to use the Massive Iot Paradigm, which suppose that there are a lot of sensors, battery powered, tiny, developed in large scale in the environment. And here, the objective is to save their energy and to split the energy between the sensors. That's the main objective of monitoring using Massive IoT. So first, we propose a framework for defining what is a strategy for Massive IoT, and also some metrics to quantify the quality, thanks to quality of receptions and also energy efficiency metrics. Moreover, we propose a specific instantiation, a specific method that ensure to have a strict reception from one of the present sensor in the environment that lead us to multi-objective problem and show that there have to be a trade-off between energy efficiency and monitoring quality. Thank you very much.
And now we have Eilat in a remote. Eilat, can you maybe unmute you and hopefully...
Yes, hello all. Can you hear me?
Yes. Yeah.
Great. So I hope this hybrid situation makes sense in the context of the room. So hey, hello all. I'm Elad. Today I'll talk about a solution we call Dynamic Deep. And basically, I hope you know that, but IoT generates massive amount of data. And the question that we want to tackle is how we can move the data to cloud services effectively in terms of costs. And in the medical domain, usually we simply deploy a static compression solution, and previous solution around compressing ECG signals focus either on optimizing the solution for signal construction performance, thus not necessarily optimized for downstream task performance, or optimized for the downstream task performance. And here in the Dynamic Deep, we suggest a task-aware compression technique, which is geared for IoT cloud architectures and ensure the IoT device stays independent from the cloud services. The compressor is trained to optimize the compression gain while maintaining the performance requirement of the downstream task deployed over the cloud services. With this new approach, we improve the F1 score of the tested downstream task and the compression performance up to 83%. So looking forward to meet you in my session about Dynamic Deep, and to feel free also to send some pictures about how the room looks like. So I will be part of this great session today.
Okay, thank you. Thank you. So we are almost on time, great. Now it's time to go for lunch.
Exactly, so we meet again at 1:30.
1:30, yeah.
Yes, and if you have some friends who missed some of the parts on the website, you already find the recordings of it. Yeah. So see you
Recording
again at
stopped.
1:30, and enjoy lunch, have nice discussions, and until later.
Thank you. Thank you. Pues acá está Armando
No, you'll see him. Last minute.
front, and he's going to present a paper, Cloud Infrastructure as a Service for Efficient Use of Sensing and Activation Capabilities in Internet of Things. Which
Good afternoon. To share
Yes. So now in Zoom,
You have to exit this one again and then say yes.
Yes, we don't see the shared presentation. If you could share your screen, please.
yes, can I share the whole screen?
Yes.
Is this one fine? No, right?
It's not presentation mode. This is actually on presenter notes.
You have the option on the top screen, those super screens, and then we'll see the correct slides.
So now it should go.
Now it's good.
Great, thanks.
Yes, now you can see it. Thank you.
Thank you very much, sir.
Oh, no, fine.
So we change the slide on the PowerPoint, but not.
Now we can stop the music. Oh, it's set. I'll check on the panel and maybe we can, maybe on the panel. Is there something? No, I just did. I didn't notice. Very good.
It's my pleasure to present the work in my lab. So I come from Concordia University in Montreal, Canada, where I have a lab where we work on 5 pieces that I can. So this is a piece of work done by one of my master students. Okay, so I will talk of cloud and how that will be used very efficiently for IoT. In the outline, some background information on cloud and also IoT virtualization, motivational challenges, the proposed architecture, the validation, and finally, the conclusion. Background information, of course, everybody is familiar with cloud today. I will stress the layer
We should just close mute.
Okay. So So the first thing here is the infrastructure as a service, which is actually the main component of cloud, because that's what allows an efficient usage of resources. And this is done through virtualization. So the idea of this presentation is to apply this concept to IoT. Right? In IoT, we virtualize the IoT capabilities, and I will be clear about this. Right, when you have a piece of sensor, there are now some new sensors on the market. So you can have several applications running on the sensors at the same time. Meaning that you might have an application collecting data every minute, another one collecting data every 3 minutes, every second. You might also have an application using the luminosity sensing capability, and another one using the temperature, for instance. It is what we do in cloud. So you have a type of mini hypervisor between the application and actual hardware. As some example, Vertino sensor, which is on the market, and Atlantic's as well. So the idea here that if you can virtualize the sensor at the node level, could you have an infrastructure as a service? We have several motivations for this. These are the challenges. The motivation first are this will allow us to use IoT capabilities in an efficient manner. And what happens today, we deploy an IoT network. And if you wish to build a new application, you just deploy another IoT network. We do not use today in IoT. Meaning that we cannot have an IoT network and several applications using the actuation and sensing capabilities of the network. This is quite powerful. That's why you can deploy an IoT network today. And in a year or two, you can deploy another application running on that IoT network and using the sensing or the actuation capabilities. It is not data sharing. It is not that you collect data and you will use. It is that you sense several applications can sense using the same IoT device. Challenge is, of course, heterogeneity, and that's why here we have several brands of sensors, including Atlantic's today, which is one of the sensors which is fertilizable. Another one is fertile. So a challenge is to have an uniform interface. Another challenge, publication and discovery, of course, because it is a network with the sensors having a wide range of capabilities. So you can imagine the sensors publishing their capabilities and the application discovering these capabilities. Another thing we know well in cloud computing is bare metal access. That even if you have virtualization, sometimes you may wish to bypass the virtualization layer, and this for efficiency reasons. And of course, orchestration. You could have several devices, and you might wish to orchestrate the sensing or the actuation, or better, the sensing plus the actuation. And the key design principle is to take what we know in the cloud today. If you take a cloud infrastructure, you have several layers in the cloud infrastructure. Try to apply this to the IoT world, keeping in mind that we have constrained resources. Virtualization in cloud is exactly not the same thing in IoT. In cloud, we virtualize resources, processes, while in IoT, we virtualize capabilities, sensing capabilities or actuation capabilities. And you see the architecture there. You have the bottom layer, where you have the IoT devices, and then you have virtual device manager. That's a piece of software which manage the devices and create virtual sensors, eventually migrate virtual sensors and delete virtual sensors. At the other end, you have what we call the bare metal device manager. This allows application to assess the sensing capabilities without the overhead created by the virtualization. You move a layer higher, then you have the orchestration capabilities. In cloud, for instance, we know that when you are creating a VM, you might orchestrate in that you may use several cells and orchestrate the creation. That's exactly what we do at the capability management layer. And the layer called the cloud management layer, it is the layer where we can orchestrate sensing plus actuation. Then of course you have the applications at the top. So essentially you have applications and this application will request sensing capabilities to sense luminosity or whatever at a given location or to carry out an actuation action, like moving the robot, for instance. Then you go through the different layers and the actual actions are carried by the hardware devices. Sure, the assumption here that we assume that these devices support virtualization. And there are indeed IoT devices on the market which support virtualization. They offer an API, and through that API you can create a virtual sensor collecting data with a frequency X. And you might create another virtual sensor collecting data with frequency Y and so on. And then you also have some sensors which support temperature plus luminosity, for instance. In reality, before virtualization, you can use the sensor for either temperature or luminosity. With virtualization, with virtualization, you can have one virtual sensor which is using the sensing, which is using the temperature capability, and the other one which is using the luminosity. Validation, we have built a prototype with Atlanticist and Vertino. We have made also some measurements of the prototype. For instance, the provisioning time, the overhead created by virtualization. And you see here a brief summary. We hope that we have motivated the need for IoT infrastructure as a service. You have to be able to use IoT infrastructure in an efficient manner, the way we do it for servers today, we have discussed the challenges, and we have built a prototype using sensors which are on the market, Atlantis and Vertigo. Our future work will be to research the progeny of IoT slices. In 5G, we have a concept of slices, which are virtual networks in the whole technology. So another interesting piece of work here will be to build virtual sensor network or virtual slices. Thank you very much.
Thank you very much. So I have a question regarding the presentation. So do you think that virtualization will still be there and to access to deal with the heterogeneity in different types of devices? Or do you think that at some point, as you mentioned, we will need to access the data resources without any virtualization layer?
Now this depends on the application. Just like in the cloud world, most of the application can cope with the virtualization overhead. However, there are very few applications in the cloud world which prefer to have a direct access. So that is to depend on the application.
So regarding the figure that you were presenting before, do you consider also Contiki as virtualization or just as an OS on the top of
Okay, so if you take Contiki, there are some extension of Contiki which support virtualization. Otherwise, I mean, the plain Contiki.
So, do we have any other questions from the audience?
So when you have a virtualized infrastructure, in the keynote we heard about data quality. And so how do you ensure that there's no change in the data in the virtualized sensor, so that it shows the accurate data that is also in the physical sensor?
Actually, the virtual sensor, just like a virtual machine, is identical to the physical sensor. The same way a virtual machine is identical to a physical machine. Yeah. I mean, this is done to the extension made to the OS.
Okay, thanks.
Any other questions?
No, for the microphone, because the remote, maybe
Yeah.
the question can be asked in front of the computer, please. Move to the...
or just be very loud, so...
Or just be very loud, yes. Or the speaker can rephrase the question that maybe...
So,
you need to go over there. So the remote part of it.
You should be on the spot.
Yes.
When you ask a question. Yes.
No, maybe my knowledge about IoT is outdated, but normally they say that IoT devices are very constrained in terms of computing capacity. So, what kind of IoT devices do you think could manage virtualization? And for which application virtualization would be a necessity? Like, because I think if you have an air sensor or temperature sensor, virtualize this sensor if it's in the same location, why would it be used? And in which cases virtualization is used?
Okay, so it is 3 questions in one. So the first question is the issue of resource constraints. Okay. And the answer is simple. I mean, that's what makes the design and implementation of sensor OS that support virtualization tricky, but it is done. There are extensions of Contiki today which allow virtualization. It is challenging, but it is done. And now, the other question is what type of application could cope with the overhead of fertilization. Let's say that you have a temperature sensor, and on the one hand, you wish to detect fire. Then it is quite clear that there you will not support the overhead created by fertilization. Okay. On the other hand, you wish to monitor the environment where temperature changes. So in that case, you can create one virtual sensor, which is for the temperature, okay, one which will cope with the temperature, and you can create another one for fire detection. So this depends. Okay. So you might have one physical sensor at the same place, and then you have one virtual sensor monitoring the environment, and another virtual sensor for fire detection. It is actually a prototype we have built.
Thank you. So thank you very much.
Thank you.
The slides are there.
So the next presenter will be Erkin. Erkin is a PhD student in the Technical University of Munich. His research interests are in the field of industrial IoT and machine-to-machine communication. So please welcome Erkin, and he's going to present the paper Resource Trade-off for TLS Secure IoT-based communication.
Presentation mode. F11, F50,
F11,
F10, F11, Somebody
is Control N. No. Right. And what? Control N.
Nice.
Oder soll die Pupa Snapchat?
Okay. And you will write 5 minutes left.
Yeah, sorry. You will speak. You have 15 minutes. When you have 5 left, I will show you 5, then 2, 1, and stop. But okay, with 5. So to prepare you to the.
All right.
Philippe, you will show.
Thank you, Dr. Potrier, for introducing me. Then, yeah, our paper is called Resource Trade-offs for TLS-secured MQTT-based IoT management. It's quite a title. I would say let's first spend some time understanding the title. I will give you the big picture, and the rest of the presentation will be very straightforward. So we will talk about, of course, IoT, and in IoT there is a very popular, actually the most popular protocol, MQTT, compared to CoAP or XMPP or other protocols. We know MQTT is most popular and most commonly used one. It's a public subscribe protocol, and it works on top of TCP. TCP secured with TLS. So in order to secure MQTT, we have to use it TLS. And we will look for how different TLS configurations, options, affect the resource consumption. What do we mean by resource? Simply CPU cycles, CPU usage, memory usage, and network bandwidth. Okay, so the motivation I already started with, as we all know, IoT is always under attack. Likewise, IoT MQTT is also under attack, and then we have to secure it with TLS. But there is a contradiction. So MQTT, most of the run, like many other IoT devices, runs on top of constrained devices. They don't have a lot of resources, they don't have enough energy, CPU power, memory, etc. But at the same time, we have to accommodate TLS. So we want to understand how we can optimize TLS, especially the Cypher Suites, the options, the configurations, the deployment of TLS, so that we can optimize the resource consumption. Let's remember MQTT. Here in this very simple example, you see one broker, two clients. At first, a client subscribes to client 2, subscribes to the topic foo. It's a topic-based publish subscribe protocol. Sometime later in time, another client publishes under the topic foo bar. And the broker has to relay this message to client 2, foo bar. If there are many subscribers, as many as subscribers, there will be more forwarding operation. So there's only one client subscribed to topic foo, that client received the message. So this is how publish subscribe in this example MQTT works. Okay. Before we start our investigation, let's learn from the related work, the key insights. First of all, of course, TLS versus no TLS. There is an extensive body of research that shows TLS is very expensive. In more detail, what we know from the related work is TLS is more cost to connect, but in order to send data during the actual communication, it doesn't cost a lot. So the connect part is really expensive. Let's say you will just send one temperature data. In order to send a single byte, you have to make all TLS handshake. That costs resource. Pre-shared key versus certificates. There is also this trade-off. Pre-shared keys are always recommended, but they are not easily manageable. They are not scalable, so certificates are easy to use. We go for certificates. Next, RSA. Okay, we want to use certificates, but which certificate? RSA, the common one, or let's say the new one, elliptic curve certificates. RSA is more expensive to sign, but we also know that for verifier, these certificates don't have that much difference. Influence of the key size, that we also know from the related work. RSA costs rise sharply with the key size, but ECC, elliptic curve, not that much. Okay, so let's take off from that point to our investigation. So what are we testing? We are testing, first of all, TLS versions as well. So the TLS 1.3 and TLS 1.2. 1.2 is the most adopted one. 1.3 is coming. I mean, this was just one click away, so we also made that comparison without putting a lot of effort. But more our focus is the Cypher Suites. So what's a Cypher Suite? Cypher Suite is a combination of these 4 categories. What are you using for key exchange? What are you using for authentication? And for bulk encryption. So how do you encrypt the whole data transmission? The combination of each of these algorithms make up your Cypher Suite. And then we did not think, okay, which Cypher Suites we should consider, and we didn't take a guess. Well, we opened the book. Iona gives the recommendations. We went to the Iona recommendations, and we created our shortlist. Key strength is another thing we have to consider. So that we had 2 options, 256-bit. Okay, this is of course more secure, but it costs a lot. We are already in the field of IoT. We wanted to go for the minimum secure one, which is 128-bit, which is deemed sufficiently secure. From the key strength, we have to go for the key sizes. Again, we follow the NIST guidelines. So nothing is from our mind or from our experience. Everything is based on the guidelines. We also come up with the key sizes. And this is the shortest. I will not go one by one because of the time. But okay, let me give you the big picture. We have typical Diffie-Hellman key exchange, and then we have 2 versions of elliptic curve. This is considered newer and better. For server authentication, we have RSA, 2 options for elliptic curve, also pre-shared key. For client authentication, we also included the MQTT's own implementation, password-based, and for bulk encryption, we have AES 128 GCM Galois counter mode and the CCM CBC counter mode. And also Cha-Cha-20 Poly 1305. From now on, I will call this Cha-Cha-20 because of the time reasons. So let's make the experiments, then let's make the comparisons. We have to pick our library. We went for Mosquito. It is C implementation so that we can get the CPU cycles better. It doesn't run on top of virtual machine like Python or Java and so on. So we can compile and run the binary. We went for Mosquito for some other reasons as well. It's the most popular one based on the GitHub stars. Okay, I know GitHub stars can be fake. There are some bots to increase this GitHub stars, but still it gives some idea. In order to get CPU cycles usage, we use the tool perf. For peak memory usage, we use the tool time. And for bandwidth usage, we use the tool T-shark, which is the command line equivalent of, they all know, Wireshark. This is how our experiment setup looks like. We have two real physical machines, so it's not a simulation, it's not a virtual environment, it's real. Two machines are running. Between them there is an Ethernet cable. The link is 1 gigabit per second. On left-hand side of the, so this server runs the clients, so whole publisher and subscribers. On the right-hand side we have the broker. T-shark, T-shark is attached to the link to get some data. Also, perf and time commands are running on the broker and the two guinea pig publisher and subscriber to get the measurement data. Okay, let's see some results. First, CPU results. I will give the summary, but more details and values are of course written in the paper that you can find and make comparisons. So for the key exchange, what we have seen is the Diffie-Hellman is really expensive. It consumes a lot of CPU. As opposed to that, elliptic curves are better, and between elliptic curves, X25519 is much more cheaper. For authentication, pre-shared key is cheaper than elliptic curve. To verify, we did not see a lot of difference between elliptic curve and RSA, but for the signer, which is actually more resource constrained, RSA is much more expensive. So RSA is not a good way to go for authentication. Okay, for symmetric cipher, we did not see a difference for small 100-byte messages, but for 10 kilobyte and more sizes, it correlates with the cipher's speed. So CBC, CCM is much more expensive than GCM, which is much more expensive than CHA-20. A hint for any hardware guy that is interested in the room, we did not use any AES acceleration, of course, because it is not common in IoT or in constrained devices always. And finally, TLS 1.2 uses few bit fewer cycles than TLS 1.3. Okay, let's take a look at this graph. Here what we want to show is, first of all, the takeaway is cipher matters. So which cipher you use makes a difference, but it doesn't make a lot of difference when you have small messages. Let's say you are sending temperature data, humidity data, 1 byte data. Well, okay, it doesn't matter which cipher do you use. But if you, of course, transmit more, larger packets, then the cipher matters. Then you should go for CHA-20 for sure. And between Galois counter mode and CVC counter mode, CCM is much more, Galois counter mode is better than CCM. Okay, on the left-hand side, we are sending 1,100 byte messages, we can say small packets. On the right-hand side, we see large packets, large messages. The difference I want to make here is for short messages, the cipher doesn't matter. You can even see CHA-20 is same as GCM, so it doesn't matter which cipher you use. But for larger messages, CHA-20 is definitely much more advantageous. No TLS is of course the best case, but there is no security there. So let's make a takeaway. For short messages, cipher doesn't matter. Again, for large messages, cipher matters. So you should gather messages if possible, then focus on the cipher. And this is for a little bit contradictory what I just said. You don't have to gather as many as possible because after some point it doesn't make any difference. So fine-tuning matters a lot. Here we are going from 1,000 to 100 messages. The change is drastic, but from 100 to 10 the change is all minimal. So you should not always go for let's gather all temperature data in one single TLS packet, like 1 year's data, and let's send it as a one. It doesn't make any difference if you just make a quarterly or monthly. So you have to tune your own use case in order to optimize your resource consumption. Perfect. So summary of the bandwidth results. For the key exchange, the Diffie-Hellman is more expensive than elliptic curves, and between the elliptic curves, X25512 is better. For authentication, RSA is more expensive than elliptic curves, which is more expensive than pre-shared key. Symmetric cipher makes a little bit difference, so you should not care which symmetric cipher you use, especially for the bandwidth. Again, same data in fewer, longer messages cost less, greatly, so you should maybe gather more packets into one for bandwidth reasons as well. And finally, TLS 1.2 handshakes use fewer bytes than TLS 1.3. Summary of the memory results, no patterns found for clients. For broker, of course, there is a difference. Smaller client certificates leads to less broker memory. The reason is every client certificate has to be kept in the broker, so a smaller certificate is, of course, better for the memory. Pre-shared key password causes least memory usage, and like the best way for the memory intensive use cases is for the key exchange you use X25512, and for pre-shared key for the authentication. Let's see some results. Here, the result I want to make here is for X25519, there is not much difference between TLS 1.3 and 1.2, but for P256, there is a difference. So with TLS 1.3, there is an extension, there is an increase in the memory. But for X25512, there is no difference. I guess this is my last result before I go to conclusion. So overall, shorter client certificate, of course, less memory, even though for same client certificates there are some difference. So the client certificate is stored for each connection. No TLS is the best case. Password, pre-shared key is of course better. Then elliptic curve is better, and RSA is the one with the most memory. So key findings. What the heck I've been talking about. The big picture for key exchange, X25512 is best in all metrics. This should be your key exchange method when you deploy MQTT with TLS. For authentication, pre-shared key is recommended if it is possible. For some reasons, maybe it's not that possible, then go for ED2551219 for authentication. Symmetric cipher only relevant for performance for longer messages. Cha-Cha-20 performs best. Buffering data in larger messages can improve the performance. And finally, TLS 1.2 actually performs slightly better in terms of resource consumption. But yeah, TLS 1.3 is never considered more secure. For the future work, from now on, yeah, you can go to different directions, even though we covered most common deployment. There are also rare use cases, like MQTT C uses embed TLS. Well, you can also make the similar comparison and then take a look at that result. Also, both MQTT, which uses both SSL, may give you different results, but they are really rare deployments. Finally, okay, let's forget TLS. How about let's make the security with the virtual private networks? Then you may want to make your security with IPsec, OpenVPN, WireGuard. This is a whole new discussion. And I want to. That's it for my presentation. Maybe I should leave this page for your questions.
Thank you very much. So, any questions from the audience?
I have a bit of.
Do you want to come on stage?
Hello, thank you for this presentation. It was fast, but really understandable and really clear. Thank you.
Thank you.
I'm not really an expert about this, but I have a question, maybe a stupid one. I don't know if you mentioned, but did you use different scenarios for, like, who were the subscriber, publisher, how many were there, and if so, did you see some real difference, like somehow, are there changes in the performance if there are like more subscriber, more publisher?
Okay. Okay, that's a good question. So for the time reasons, I did not include more details about the process of the experiments. But so most of the experiments, for simplicity, we use one publisher, one subscriber to get the measurement data. For the broker results, of course, we used, I guess, more than 1,000 brokers and publishers and subscribers in order to scale at the broker to get the measurement data. So we also consider different scenarios. I mean, in the paper you can find them, but for time reasons, I did not include here. But that's for sure, we include them.
And also, I have a very good question. And what do you think about the security of Cha-Cha-20? So if you compare Cha-Cha with IES.
Yes, very good. So let me start with a disclaimer. We did not care that. We base on the IANA recommendations. IANA says that Cha-Cha-20 is secure, we take it. If it is not secure, we did not take it. My personal opinion, of course, when I was doing these things, I was also reading about the ciphers, even though I'm not an expert in cryptography either. So I'm just using the IANA recommendations and NIST guidelines. Yes, Chacha 20 gives the same security as IES and using less resources and faster because of its own algorithm. This is the thing as far as I know. And it is secure, I say this based on the guidelines by IANA.
Yes, and also in your setup it was working much better than IES because you were not using the acceleration hardware for...
Yes, exactly. We did not especially use the acceleration because acceleration is not possible in all IoT devices. It's really rare. So we should not expect this acceleration. It may be a game changer, that's for sure, for AES. We disabled that.
I have some questions related to this. Thank you. Great. I like to see real numbers.
Ah, nice.
But okay, my question is, don't worry, it's not, we know that Chacha was made for software and AES was made for hardware. So you did a software-only comparison and you say it's uncommon, but we have more and more Texas Instruments. Now almost every chip comes with AES. What would you expect if you have the hardware to do AES? Well, it's no question. How many orders of magnitude? I mean, if you have the hardware, you should use it, right?
Yeah.
And the advantage with Chacha is because the software you can adapt. Tomorrow is not more valid, you change. The hardware you cannot easily change. So this is more perspective, what you think. I work with constrained IoT, so in my hypothesis, TLS, TCP is too heavy. We even use UDP, DTLS, and we use co-op. This is lighter than MQTT. It's lighter. Everything is, but not everything because you don't have the message arrangement. But what would you expect, or could be future work to say why you should use MQTT and TLS? I know they use it because it's easier. I mean, if you support it, it's better. How do you see the future? You think it will coexist, co-op and MQTT and DTLS, TLS, or what do you think about this?
Yeah, okay, very good question that opens several discussions. Let's start with the first one, with co-op on top of UDP, whether it is better alternative for TLS on top of MQTT on top of TCP. Actually, that's a work in progress paper of mine right now. I'm writing. So we switch different transport protocols, TCP, UDP, and see the influence of them. And your question regarding how is the future of TLS, will it still exist or will it be replaced by co-op? Yeah, okay, this prediction is not that easy to make. One thing for sure we know is MQTT is used much more common than co-op. There are many metrics to say that. MQTT is used a lot more comparable to co-op. And co-op, okay, it's older than co-op, but still co-op has been around for 10 years now maybe. So still it doesn't, it's not a game changer so far.
Okay.
And I would say definitely MQTT will also persist because if you need a publish subscribe protocol, then co-op is not always easy to use. There are also some practical problems with the co-op because co-op is not designed for publish subscribe. It is just like an HTTP alternative for constrained devices. When you need publish subscribe, which I showed in my second or third slide, you should go for MQTT.
Great.
It works. It is lightweight. Yeah. The only problem is, as you said, with TLS, TLS it has a lot of problems. It's heavy.
Yeah,
it's heavy to accommodate.
Okay. Well, thank you. I think we give again an applause to I take the relay now. Yeah. Now Filippo will be presenter, so I take the relay. I am the session chair for this. Originally we had a small break, but to keep on time we won't do this small break, so we will just keep with the flow. Paper session 2, so 15:30. Maybe we can do the break. What do you say? We have 7 minutes. Not enough?
No, it's too plenty.
We can do just 5 minutes break.
Sorry, no. We are behind schedule. So we have 2 more presentations. First gonna be Filippo. I will introduce later, and then we have a remote presentation from Elad, and then we do the synchronized break with notes. Let me look for the bio of Filippo so I properly introduce you. Filippo.
Or let's make the 5 minutes break and just go 10 minutes into the coffee break.
Sorry?
We can also make 5 minutes break and then go into the coffee break.
Later? I don't know. What do you prefer?
Who prefers breakout? Nobody? Okay, now we continue.
We continue, okay. Dr. Filippo Poltroneri received a PhD degree from the University of Ferrara, Italy in 2021. He joined the Distributed System Research Group led by Professor Cesare Stefanelli in 2017. His research interests include distributed systems, IoT, fog computing, and tactical networks. He has been visiting the Florida Institute for Human and Machine Cognition, HEMC, in Pensacola, Florida, USA, in 2016 and 2017 and 2018. And Filippo, I don't have your slides.
Yes.
No, thank you very much. So, 2 minutes setup time, sorry for this, as usual. I just unplug this, but NTFS is good. It won't corrupt my file system. Okay, this is the right choice for those who speak Hungarian. I think.
go for it.
No.
Format the stick one.
This is it, Filippo?
Yes.
Not presentation.
No, I guess that one is
The other, okay. So, Filippo is here. Water. Very sexy title. Sorry, I didn't say the title of what Filippo will present. It's Water 4.0, enable smart water and environmental data metering. So now I'm going to share in the Zoom. Too many windows. Sorry for the remote, for everybody actually. Let's share everything. It's not PowerPoint, it was Control L.
no, that one is Microsoft Edge, so it's open. And then Control L.
Looks good.
To share the screen.
It's already sharing.
Okay.
Somebody can-
Close.
I know. We have a question? Yeah, sorry. I didn't check the chat. No, if you have it. The floor is yours, Filippo, sorry.
So thank you very much, Henry, for your presentation. So the title is Water for Zero, enabling smart water and environmental data metering. Water for Zero because is related to the industrial IoT, which is also called Industry 4.0. I mean here because this work is the result of the collaboration with private company and also other companies with which we collaborated in the past for this topic.
Not working.
So yes, the motivation about this paper. So we know that environmental pollution is an important problem nowadays. Also, we have the pollution of water resources, and which worldwide cause many deaths and so on. And also, we have another problem, which is the waste of water resources, which is very high, especially in Italy, and also in the Sicily region where our partner is located. So, in order to reduce the loss of water and also to monitor the quality of those resources, we need to investigate, to propose different environmental monitoring metering solution. So, why we call them smart? Because the idea is to apply as much as possible IoT technologies because they are great when you want to, for example, reduce also the operational cost. Usually IT devices can come at a reduced price. If you compare the price of the sensor, I don't know, the sensor that you might attach to Arduino devices or Raspberry Pi devices, to the sensor, to industrial level technology that you buy from Siemens and so on. So the idea is to apply IoT technology to the development of a metering platform which can collect several IoT data, and also to analyze those data to provide useful information to environmental agency and so on. So this is a typical scenario, typical smart metering scenario. So we have several data to collect. For example, consumption data. We might have these meters that collect the consumption data at different points. Also, we have sensor like flow, velocity, temperature, pressure sensor, which instead are distributed in different parts of the water distribution network. So, for example, close to a pit or whatever. And usually, smart metering platform use low power wireless and also communication protocols such as wireless bus and LoRa, which use the unlicensed spectrum, so they don't need to actually have a SIM card or we don't need to rely on a telco provider to send those data. And then we also have a cloud. Generally, we have a cloud part, which is the one where the processing of the data is actually performed. Realizing this kind of platform is somehow challenging because we have to deal with, for example, the interoperability with different devices. I already cited the different communication protocols, so we need to support different protocols with different data format. Also because each sensor comes with its own technology. You have a lot of vendor lock-in, so if you want to be open, if you want to support multiple type of data, you need to concentrate a lot of masquerading the heterogeneity. And also, another challenge is to support the modification, which means to be able to support new type of data and also new devices in the future, because you don't want to develop a platform which then stops working when you need to attach another type of device. So we started to work on this project, Water 4.0, which main goal is to develop a platform, a comprehensive platform which is capable of collecting the data at the IoT level and also to analyze this data. Here we also wanted to provide information about the quality of water resources, so we analyze both the consumption but also the quality of the resources. The solution that I'm going to show you try to address several requirements. Among them, we also have the necessity, the requirement to update IoT devices. So, for example, we have different gateways at the IoT level, and we want to be able to upload their software to integrate the gateways with some other software component that can process different kind of data. So this is the overall solution that we propose within this project, and we have different parts. So the first one, the field part, represents a generic installation of IoT devices and of IoT sensors. So you can see different types of devices, and also a data decoder block, which is usually an AC/DC converter, which reads data from raw sensor and convert signals basically into computer readable data. And then we have those IoT processing gateway, which main responsibility is to collect the data from the different sensors. So we have different IoT gateway, different IoT processing gateway, one for each field. And then we have the cloud part, where we do the processing of data. The field, the edge, and the cloud communicate using the cellular network. So, for example, LTE, 5G, or Wi-Fi. The processing gateway has a Wi-Fi connection, and all the communication is done via MQTT. So the processing gateway here, as the name says, act as gateway, but it also aggregates the data coming from the sensor. So it's not just a relay that sends all the data that is reading from the sensor. Basically, it does some processing of the data, and also it aggregates the data, and then we send the data at a regular interval to the cloud platform. On the cloud side, instead we leverage on AWS technologies and software and services to build an analysis platform which could be very extensible by supporting also serverless computing. So the idea is just to send the description of the platform, and then if a provider needs to do customer operation, you can deploy his own server function to the Amazon Lambda service platform. So, as I was saying before, IoT processing gateway are very important in this project, in this paper, because they do multiple stuff. So they read all the data from the sensor, and they also process the data, and are responsible for communicating all the data to the cloud platform. Instead, here is the list of services on which we leverage for creating the analysis platform. So we have IoT Core to manage the connection with the IoT devices, the IoT processing gateway, MQTT, Lambda for deploying the service component which actually process the data. So, for example, the pressure or the consumption that were registered at different installation points. And then we have also, of course, a database to store the data and to make them accessible to some user, which can be environmental agency or even residential user that want to check the status of, for example, their consumption, but also the quality information of the water in different city, municipality. So here we have just an example of a dashboard that we created using Cockpit, which is the cloud visualization layer. And you can see different kind of data. We see the pH, for example, the pressure, and other kind of data that we collected using the platform. So this one is just a simple dashboard with that we realized using a bulk mock-up installation that we used to test the validity if we were able to collect the data and also to analyze the data. And so just to show that we can actually display the data using a cutting dashboard and also the information. So the last part was about the software that is actually deployed on the IoT processing gateway. So to be able to ship over the air update, we developed the old software using Python. Here we have different models that take care of, for example, interacting the database, reading data from a serial port, or also reading data coming from the USB stick that has the LoRa receiver or the wireless and bus receiver, and all the other functions. We decided to simplify the solution. We decided to ship all the solution as a single container. But we have three main functions. You can see them on the top. They are the green ones, so collecting, cleaning, and sending. They are basically to collect data from sensor, do the operation on the gateway. So aggregate the data, label the data, and send data to the database. And also the sending one is the one that interacts with the cloud services on AWS. So we ship all this data as a single container, and we have three different entry points. which we use to start the different rotations. And for the overhead, the air update, we relied on the Mender, which we find to be an open software solution, which in our case was very efficient and very easy to use. So we built a system that leveraged Mender to ship their data to different IoT processing gateways on the field. So thank you very much. So to conclude, I just wanted to say that we didn't present an actual experimental validation, but we are planning to do a very large-scale validation of the platform by deploying several installations, and so we can have a very detailed analysis also on the validity of the platform, but also on the cost that such platform need to. So I mean, from a service provider perspective, the cost that such data platform would have. So if it's better to use IoT technologies or instead of relying on industrial collection solutions. So that's it.
So now is the question session. Please, any question in the room, come to the front and speak Filippo face to face. Do you have any questions? Mark Oliver?
So, what was the biggest domain-specific challenge in that setting?
Oh, so the main one, I guess, was to collect the data from different sensors. So basically to interface the sensor with the Raspberry Pi, which we use as a processing gateway, but also to, for example, to write the software to parse the data, since we had a lot of sensors that was very hard. And also from the collection part, it was sometimes difficult to read data using the plain LoRa or the plain wireless bus, because we for this project we didn't rely on LoRa one, so we didn't use the infrastructure but just a plain protocol for reading the data. Because what we experience is that so even if they are supposed to be very long-range protocols, sometimes these sensors are located in very I don't know, in bits, so they are not able to transmit data at very distant locations. So you should try, you should place the processing gateway, the collection gateway very close. I mean, not very close, but you should optimize the placement point, the deployment point.
Thank you. More questions from the room? No? Maybe I have a question. Amazing framework, Filippo, especially because apparently it's running code. So great and running on top. So you say future world is applying, but for even bigger scale. So what was the scale of these experiments you made?
Oh, so the data was coming from a Mac installation that we had. We also don't have a large experimental setup now because we have so the collaboration that we have with the company doesn't let us to
maybe I can answer that. It's a major Italian project, and we are developing the infrastructure both at the environmental quality level and at the water metering level, which is not covered here. But the problem is that the companies are behind in giving us access to field data. So we're ready with the infrastructure, and we don't have the data because the companies are struggling behind.
Okay. So in the end, this will be, the company will apply this to their own water infrastructure, let's say, Even if it's open protocols, they will do what they, it will be a private framework, let's say,
There are also some other universities in Italy that are especially developing sensors. So they're going to this major project that spans from the development of new sensor types to the collection of, to the identification of when to measure something. Because of course, in the previous presentation, the colleagues showed us that you have to reduce the number of sampling, to minimize the number of sampling. So that's a major project, and this is the first part of the presentation.
Thank you, Filippo.
Okay.
So thank you. Now we have one more presentation before the break. I stop the sharing. Elad, I see you are ready. Great. I'm gonna read your. You can start trying to share, but I'm gonna read your bio first. Full screen. How would I do full screen? Great, Elad. Give me 1 second that I find your biography and UMA. Elad. Okay. Sorry. It's okay. Now we are going remote presentation. We have Elad Wasserstein. He's going to present dynamic deep, tune ECG task performance and optimize compression IoT architectures. Elad holds his Master of Science, MSc in Computer Science and Computer Engineering from Reichman University and Ben Gurion University, respectively. He is active in the areas of cybersecurity, compression in IoT environments with involvement in AI and big data technologies. After several years of building cyber prevention systems, in the past year, he joined Meta, previously Facebook, to help engineers solve problems, predict future events, and reach relevant data more quickly by pushing Meta's infrastructure to be smarter and capable of learning from previous experience. Thank you, Elad. So the floor is yours. You have 15 minutes and then 5 minutes question.
Great, thank you very much. What is the chance we can also turn the camera so I can see the audience?
Yes, good idea.
Great, so good afternoon everyone. I hope you can see me and you can see the slide.
Give me 1 second, I put your... okay, yeah, but maybe it's too big. Okay, maybe we can work with this. Okay, yeah, we see you now. Sorry, now.
Great, thank you. So this is a joint work with Eli Brosh and Anand Bremer-Bar, and let's directly dive into the problem statement and the motivation behind this work before we dive into the details of implementation and the results. So, in IoT cloud architectures, we deploy heavy computation downstream tasks over cloud services. And in this work, we focus on IoT medical architectures, sensing ECG signals that monitor the health activities of patients in hospitals. For evaluation purposes, we use 2 downstream tasks. The first one is the ability to classify heart rate arrhythmia, and the second one is the ability to extract features from ECG signals like RL peaks. Now, to make sure the process of sending data segments from IoT devices toward cloud services is effective and reduce cloud cost to minimum, like maintaining centralized EV storage over cloud services, we also integrate compression solutions, a compression module over the IoT device, and a decompression module over the cloud services. And now the decompression module is responsible to reconstruct the signal back to the original representation. Now, from those compression solutions, we have 2 main requirements. The first one is having high compression performance, which we evaluate with the compression gain metric. and the compression gain method then checks the ratio between the original representation size against the size of the compressed one. And secondly, we want to make sure that there is no performance degradation in the downstream task when using the output of the compression solution. So in the next slides, I'll show you a new approach to solve dimension, but before that, let's see how previous work solved this. Previous works for solving the compression challenges in IoT cloud architectures suggest two main approaches, lossless and lossy. The lossless approach guarantees not to suffer from information loss, and indeed when running LAMP-RZIF 77 over well-known ECG dataset, we didn't encounter any performance degradation in downstream tasks, but achieved a low compression gain of only 2.7. As opposed to the lossless approach, the lossy approach allows us to lose information, thus has the potential to reach higher compression gain, but this comes with the cost of lower downstream task performance. And indeed, when we apply the state-of-the-art convolutional autoencoder over ECG signals, we reach high compression gain of 32.25, but this came with a reduction in heart rate arrhythmia classification performance from 0.87 to only 0.2. Now, these previous work that aim to solve the compression challenges mainly focus on optimizing the reconstruction task. Thus, are not necessarily optimized for additional downstream tasks deployed over the cloud services, or even those that we have tested here in this work. On the other hand, we saw a lot of work suggesting optimization for specific downstream tasks, but then those not lend themselves to solve the compression challenges. And this is exactly where dynamic deep comes into play. In dynamic deep, we suggest to close this gap by balancing between the compression performance and the downstream task performance. The system administrator will have the power to balance between the two by choosing the upper bound error of the downstream task. Given this configuration, we optimize both compression performance as well as the downstream task performance. Additionally, we suggest to adopt a dynamic way of thinking when compressing data segments sent from IoT devices to other cloud services. And by doing so, we successfully improve the F1 score by 3 times, the recall by 4.5 times, and the compression gain by up to 83%. And having a dynamic way of thinking is not so trivial when we talk about IoT setting. And the main challenge and the main question that comes up is how the IoT device can decide for the optimal compression level and still staying independent from downstream tasks deployed over the cloud service. So let's try for a second and let's neglect this challenge and see what happened, and let's understand why we need this dynamic way of thinking. So let's assume the contrary and assume we don't want the dynamic way of thinking. Now, to allow the system administrator configure upper bound error for downstream tasks, we saw that for a low configure upper bound, there is no static compression can satisfy it for every data sequence. This is why we believe, and this is why we went to the direction that we need to optimize the compression gain per message. And let's see how this is coming to play here on the box plot on the right. So on the box plot, you can see here the axis represent different compressors, that each compressor has a different compression gain, from compression gain of 128, 64, 32, 16, or non-compressing at all. And on the y-axis, we can see the categorical cost entropy loss for the heart rate arrhythmia classification task. And we measure the error for each data segment sent from the IoT to all the cloud services. And let's take this horizontal blue line that the system administrator configured, that it doesn't want the downstream task passing this upper bound error. And we can see that there is no single compressor that can satisfy this requirement of the system administrator. The compression gain of 128, he has here a lot of data segment that doesn't satisfy this requirement, also the 64, 32, and 16. This is why we believe we need to always jump from one compression level to another compression level to always make sure we satisfy this upper bound. So I hope you understood the challenge and the motivation behind deploying compressing solution in IoT cloud architecture. So let's see exactly what is dynamic. So dynamic deep is a lossy compression method in which the system administrator can control the desired performance level, and the performance level can be chosen from a wide range of performance level that the downstream task can perform in, and maintaining an optimized compression gain that is geared for cloud systems. So let's see how we achieve that. So we extended the existing conventional autoencoder that had a static compression gain of 32 with additional 2 compression level, compression gain of 64 or no compression at all. Now to turn the average device to be task aware and reduce the need for feedback from the cloud services about the downstream task error, we added some dense layers to the compression module that learn to predict the downstream task feedback for each compressed representation. The ability to predict the loss together with the pre-configured upper bound error turns the decision about the optimal compression gain be trivial by simply choosing the compression level with the highest compression gain that meet the upper bound error. And lastly, since we are talking about the deep learning architecture, we also need to define the loss functions. So here, since we want to optimize both for the reconstruction signal task and also for the downstream task, we simply combine, we propose here an additive loss. We call it the loss combined, which takes into consideration both the reconstruction and the loss weighted. And the loss weighted is simply a linear combination of all the losses of each downstream task. Now we multiply each loss with a weighted factor just to make sure all the losses perform with the same scale. Now, now that we understand like the technicalities how dynamic deep looks like, we also want to make sure that we can deploy it for on IoT devices. And here we didn't make any exciting thing. We simply use well-known techniques in the world of deep learning to reduce the number of parameters, so we can be effective in terms of memory and computation resources. But without going into much details, we perform two main steps. The first one, instead of simply deploying multiple compression modules for each compression level, we share layers between those compression modules to make sure we don't we calculate the computation and the memory only one time for each compression level. And secondly, we also reduce the number of parameters and preserving the receptive field characteristics of those convolutional layers by applying well-known techniques that were published in recent weeks. By doing so, we successfully reduced by 67% the memory requirements compared to the state-of-the-art convolutional model. So now, the only last thing that I need to show you and convince you is that we dynamically actually allow the system administrator control and balance between the compression performance and the downstream task performance. And to do so, what we did is to create a theoretical feedback-aware method. As I mentioned previously, in IoT settings, we don't have the feedback from the cloud services. Thus, this is why we added the denser to predict what would be the downstream tasks over the cloud services. And so for the evaluation purposes, we coupled the IoT and the cloud services together to have a quick feedback about the loss itself. And here on those graphs, we can see on the left side, we have the average compression gain as function of the upper bound error configured by the system administrator. And on the right side, we have the effective task loss as function of the upper bound. And first, we can see that once the system administrator choose a higher upper bound error, this immediately allows the effective task loss be higher, meaning we allow to lose more information in the process of sending data segments from IoT devices to other cloud services. And since we allow to lose more information, respectively, we can see that the compression gain also is increased. And vice versa, if the upper bound error is tuned to be really low toward the left side of the x-axis, respectively, the compression gain is also reduced. Now this graph really shows that dynamic deep successfully follow the behavior of the theoretical field-aware methods and basically allow the practitioners balancing the compression gain and the task performance. Last but not least, we also did some cloud cost reduction analysis, but due to time constraints, I won't go into much details. But basically what we did is to take into account the expenses of the decompression model computation, the expenses of the storage, and also the expenses of allowing staff members to review what happened in the data over the cloud services. And the bottom line is that for one hospital with approximately 200 beds, they can save up to 97% in their cloud expenses by integrating them. So to conclude, we saw that optimize for downstream tasks is a key idea to improve compression gain, and the dynamic diff allows practitioner balancing between compression gain and downstream task performance. For future work, we believe that we can improve further the compression gain performance by using past data segments and leveraging stochastic characteristics, and we believe that we can also transfer this approach to additional domain. So thank you very much for listening. Feel free to scan this QR code and get immediate access to the paper and also to the code itself. And questions?
Thank you, Ela. First, thank you very much. So now, some questions in the room. Please come in front here to us. When? Yes. Shall I? Yeah, I will focus on you.
Yeah. Thank you. It was really interesting presentation. Sorry, but I just arrived a bit late. May I ask a question about your metric? What does exactly mean your downstream? Like you are about like compression of data using deep learning, if I'm right, and like what does that mean exactly? Downstream tasks.
Yeah, so downstream tasks can be anything that will be run over the data that was sent in the IoT device. So for instance, here in this work, we use ECG signals. ECG signals are electrocardiogram, and basically they measure the heart activity of patients in hospitals. And we use here two downstream tasks. The first one is heart rate arrhythmia classification, and here the metric is the F1 score if we successfully classify the arrhythmia correctly. And another downstream task that we evaluated on is the ability to extract our peaks from ECG signals. And here the evaluation metric is as well the F1 score. Basically, is if the downstream task performed well or not.
Oh, okay. Okay. Yeah, now I get it. Okay. Thank you. Really good job.
Okay, any more questions from the audience? Maybe I have one. Okay, good. So yeah, great work, Elad, and very useful for hospital novel cause. So so you do compression at the IoT devices or at that side. You show us that you you have lightweight RAM consumption, but what about the CPU or the capabilities you need to implement at that part of the system? Is it possible, I mean, current hardware is able to support your proposal, or we still need more hardware? I think in the long run, even if you need more expensive hardware, it's beneficial because it's more expensive to store data. But so you have some insights on how feasible it is to implement this on real current hardware?
Yeah, so this is a great question, and basically every task has different requirements of IoT, and in the world of deep learning there is vast work about bringing models to IoT devices, and by simply applying techniques, and we saw that there are some IoT devices that, given those parameters, we can very easily deploy those on those devices. Let's say that we have the Raspberry Pis and we have the Arduinos, but we didn't evaluate for more lightweight sensors. But for those scenarios, what we thought of is basically if we have a lot of sensors in the hospitals, usually we also have like edge devices on those hospitals, and then we can aggregate and collect everything to those edge devices, and then from there apply that.
Thank you. Yeah, because I'm thinking about normally if you are an IoT device, you have low energy, so you save up energy by sending less data. That's one game. On the other hand, if that's not an issue, maybe you can do the compression at the edge or at the cloud. Why you do the compression at the edge to leverage maybe the effort from the other side, I guess, or maybe you can be hybrid. In the end, doesn't matter where the compression is done as long as it's done, I guess. Basically, I didn't ask a question, but could make sense to not compress at the edge because maybe transmitting is cheap and compressing even at other part of the system, or not?
Yeah. Actually, we also had a lot of arguments for that. One thing to keep in mind is sometimes the IoT devices are deployed over 4G and 5G networks, and the costs of the network bandwidth is we also need to account that. So this is why maybe it makes sense to deploy it on the edge device or on the IoT device. But if the network bandwidth is really cheap and free, and we don't have restriction around like sending the network in itself, maybe we can also deploy it over the cloud services. It will depend on the application.
Okay.
Yeah. Maybe just.
We have another. Thank you, Ella. That's all for my part. We have more questions from the audience.
Yeah.
One again.
Me again. Sorry. Did you try to like compare if it was more economical, like in some use case, to compress rather than just send the data in terms of battery saving? Like I know that, for example, for instance, doing this compression can be easy in terms of computational things, so it's consumed energy, but maybe it saves more than just sending all the data. Did you check about this, or is it about future works?
Actually, this is an interesting idea. We didn't measure like the CPU, like the CPU cycles are pretty constant in this solution, but we didn't measure like the CPU cycles required for transmitting the compressed data against the CPU cycles required to send the uncompressed data. And this is an interesting also thing that we can consider. Basically, we believe that since there are vast works around integrating compression solution, there is a beneficial, but definitely it's a point worth.
Because in that case, you can apply it to like really constrained data, constrained sensors, I would say, and say, okay, even if I need a lot of memory to do these computations, it saves some energy to do this compression and to send everything in the cloud. Thank you.
Yeah, thank you very much.
Thank you very much, Elad. We're gonna close the session and go for some coffee then. Once again, an applause for Elad. Okay, see you later.
Recording stopped.
Thank you,
Slightly bending over.
Yes. At comfort.
Yes,
okay. If you need a lot of that, and will it be here?
Yeah, I guess.
Okay.
Yeah, it was good. But I was missing you on Tuesday.
Last Tuesday.
Yes.
Yes. So what happened is.
You forget about it and you slept anyway.
No worse, I did not forget about it. I felt lazy about it. So I was completely aware of that. I just wanted to say be silent and then they will forget me, etc. Immediately, Professor Palot, you are missing.
Yeah, completely different. I wanted
It
to
was
go there,
not ready either.
but I totally like.
I did not forget, I was aware of it. I just felt lazy. And yeah, I didn't just show up. Also, my slides were not ready.
Were not?
Were not ready, my slides.
I know everything was ready. I also uploaded the video and so on.
They look very, no, they were clean, so it was okay.
After your question, actually, it is again like one click away. Why didn't we enable AES acceleration as well? We have 5 results, disable, enable. We could do that easily. Why didn't we do it? That's true. It's so easy to do.
Yeah. We know.
Then we could have the results as well and compare.
And to see for how much.
Exactly. Yeah, very simple thing to do. Why didn't we do it? No idea. We forgot.
Supposedly, it should win, but I think it will win against software. I should win because
I don't know.
hardware must be. But I know I use Chacha, and I know this Chacha is very good.
Chacha is also approved by Mr.
It by standardized. I don't know. Maybe it's approved, but it's a guy who designed it.
Yeah, I remember like, some years ago I was working on security, and I remember that I took a survey or just a simple one, not a very.
Sorry, Christian. Yeah. Okay. Nice to meet you, Renzo. I will collect. You have yellow. Sorry.
Yeah, no worries.
I will collect your presentation on.
We went for I did not check NSA.
by Arnaud Lemeaux from IMT Atlantic. Please come forward.
IMT Atlantic.
Yeah? No?
IMT Atlantic, France.
That's you. Yeah? Please. You're talking, not me. So 15 minute slots. And Renzo is in charge of. I will show you 5, 2, 1.
Today my presentation is talking about enrolling for IoT.
You have to talk louder.
Loud, please. Yeah.
I said today my presentation talk about federal roaming for IoT roaming, for IoT using private DNS resolution. We show you how DNS will be used to do the roaming between different IoT operators. To do this, firstly, we will define the importance of roaming in the IoT network by talking about their application in every day. Secondly, we will talk about different architecture of roaming existing in literature. Third, you give your purpose method. Four, you give the performance, and last, you conclude your work and give the perspective. LoRa Alliance is an open association that developed the standardization of LoRaWAN technology. They introduced in 2017 in specification 1.1 roaming. Roaming give in the device the capability to change the operator, to change the IoT operator. Now you have 150 operators in the world that use this technology in 163 countries, 20. You have many applications of roaming. You can use it to tracking a parcel, to a smart transport, to research work define what DNS can be used to do the roaming. The first work is Hamnash work. Hamnash works. The author proposes you the new method or device, the new method, and it gives on the device the possibility to use the DNS to change the operator. You can see when the device it's mobile, you send the request in the LoRa gateway. LoRa gateway contact the home network server to have the information, to have if it's possible for you to connect in the another operator. The master agent is used to have a net ID, of the device. The net ID is identified of each network server we can use. If you want to have the net ID, in the net ID, if he like to have net ID, you do the resolution, the DNS resolution. In this work, this resolution is not secure. You don't have the security to have a net ID. So it's possible to have a man in the middle attack. The second one is a EOT run. EOT run is proposed by IFIP. In this one, he show again how DNS can be used to do the resolution. Why he chose DNS? Because DNS is an essential infrastructure today. Is used today to resolve the interoperability problem in the internet. In this architecture, he show again how the device can do the roaming. Firstly, the device send the join request in the LoRa gateway. The LoRa gateway transfer the request of a network server. The network server extract the join UI contained in this request and contact and send the message of the DNS. The first message sent is DNS resolution to have the IP address of another IoT network. The DNS resolution can be returned by forwarding network server. If everything is okay, it gives the possibility of the device to contact the operator network by another operator network. The problem you have in this architecture is, firstly, the owner device need to provide to have a join UI. If the join UI change the operator, owner device, this device can refresh, can change the join UI. This operation is the cost of this operation is very big, and the join server who can use to have join server who have the information, the setting, the security setting of the end device is very exposed, and the author used a certificate to secure the communication between different operators, and this certificate, the provision of this certificate is very centralized. We propose now a new architecture. This architecture is use DNS, but the method of provide the certificate is very decentralized, and you add a new component named broker, DNS broker. The DNS broker give the possibility of the owner of device who like to do the roaming to save the parameter of the end device. If the parameter if he like to do the join request, you have to do the roaming. You have a certificate. The certificate value. The certificate have the period, the validity period. Now in the resolution, what the resolution work? Now if you want to do the resolution to have the information to have the IP address of the join request, you will have a certificate. To do this, you will divide the resolution in two pages. The one page, you will do the resolution private, your private resolution. The second page, you will do the public resolution. The page that you use the private resolution, you use DNS over HTTP. DNS over HTTP is the new method you use today to encrypt the message of DNS, to encrypt the message sent by the DNS using the certificate. Okay, this is the new architecture of the broker one you redevelop. You see here the device when the owner likes to do the roaming. You set all the parameter of the broker. If the device likes to do the resolution, you will have the certificate, the valid certificate to do it. This is your provision of your certificate you develop to do this resolution. The first resolution I explain is the first certificate is used by the owner device to contact the broker who have the parameter of the device. The second certificate is used by the different IoT operator. You see that the different system is very decentralized. Okay, now is to implement the implementation. You use Shifter platform. Shifter is open source platform you can use you have possibility to develop your network server, and you use to those servers who generate the certificate to secure the communication during the DNS resolution. You use DNS proxy, and your experience is good. You have this result. You compile your result in the existing architecture proposed by AFNI. Now you use Wireshark to analyze the different exchange. The first exchange is DNS resolution. The DNS resolution, IoT is the architecture proposed by AFNI. You see, the architecture proposed by AFNI using DNS, you don't use the certificate. Now, to do the resolution in your architecture, you put the certificate, and you can see the different engine. The second engine you can analyze is HTTPS. And it's a HTTP. You do many join requests. To see the engine when you can see many of packets and the different exchange we do. Okay. To resume, you implement this architecture using a Shifter. You develop a new method. You replace in the architecture to do the roaming. The author of the existing architecture use the join UI. Now you use a dev UI. Dev UI is identified by the identified of a device. You implement your method and use Shifter code, and you add the new component is broker to control the different exchange different exchange is during the resolution. To be due in the future, you will show that during the resolution you have HTTPS. HTTPS generate many exchange. In the device is not good for the device. You will replace HTTP by QAP. QAP is very good in this architecture, and you will propose a new the TLS who you can use here. You can replace it by a doc. A doc is a new standard developed now to replace a TLS exchange. Thank you.
Thank you, Arnaud. Has anyone got any questions for Arnaud?
I have some if nobody has.
Yeah, please. Yeah.
Thank you, Arnold. Yeah, I know this is a big and promising application to do roaming, data roaming. One question that was not clear for me that maybe you can clarify. So this solution you propose to do LoRaWAN roaming is compliant with the LoRaWAN standard for doing roaming, or needs an adaptation?
LoRa, the method proposed by LoRa Alliance, who developed the LoRa standard, is use a DNS, classic DNS, the simple DNS resolution to do the roaming.
Okay.
And this method is not secure. You don't have, during the DNS resolution, it's possible for attacker to intercept the communication and
yeah, explain this. Yeah. So, okay.
Now you propose a new method to secure this communication using the certificate, and you add a new component named broker, which gives the possibility of the owner, device owner, to save the parameter of the device during the resolution. Secondly, you will replace join UIs proposed by LoRa Alliance by DevUI.
Okay.
Join UI is identified of the net ID, and if when the end device want to do the roaming, you use this join UI. But if you change the operator, if the owner device have 1,000 device, he will refresh. He will refresh hold the device. This operation is very, the cost of this operation is very
okay. So
you propose now to replace join UIs by the by dev UI. Dev UI is identified by the device add by the period in fabrication.
yeah, unique manufacturing. So to recapitulate, we need to modify a little bit the standard, but the gains could be. I have another question, but maybe if there is.
Yeah. Does anyone else got any questions? I have a little question.
Okay. Yeah. Go
Oh,
on.
thank you. So it wasn't clear to me whether you're using DNS just to resolve a host name, or whether you're adding extra fields to the DNS entry that will then be returned to the caller.
Can you repeat that slowly?
Okay, so with DNS, there are some standard fields, AAA, some others, yeah?
Yes.
In your system, are you adding a new field to the DNS record?
Yeah.
Or are you just using the standard fields but looking them up in a different way?
I use a standard field, but I add a certificate to secure the exchange.
Okay.
You don't understand
Yeah, sure, yeah.
I add now is a certificate to secure the exchange. This method does not exist.
Yeah, okay, that's good. Thank you.
A small question. So you presented us with some performance results. You obtained this by doing what, simulations, or you implemented on LoRa hardware? You show us our architecture, so I guess how you obtain these numbers, you have both solution and then you measure?
I use the icon, I use the, we modify the shifter code, and we use a PyCom as a device, and the Pygate as LoRa gateway, and you send the menu join request. You send the menu join request, and you in the network server. You put Wireshark to
So it was real platform. Yeah, sorry.
to create the action and compare the result.
Great.
Thank you. Yeah.
Thank
Yeah. You have to drive Windows on a nothing.
We will stop the presentation. Okay, so it's disconnected. That's
good.
Okay, let's. We have time because we have a flexible schedule. Or only remote or I think we're good to go. This is a pain. Yeah, this is a pain in the ass, as you know.
Don't worry. Hi everyone, our next talker is Christian Lupin. Please. So 15 minutes for talk, and then when time people
for remaining time.
Thank you.
Yeah.
So as I said, my name is Christian Lupin, and co-authors of this paper are Simon Schäfer and Margareta Pahl. And within this paper, we are in the
You are in the, sorry.
you need to click
Yeah, okay. And this may work.
Okay, yeah, and within this paper we are in the IoT. So I just printed some devices here on top. So as we also already heard today, and as you already know, the IoT experienced a great growth in performance throughout the last years, and we have the Raspberry Pi on that. That's just one example for one quite powerful IoT device at the moment, having, for example, up to, I guess, even 8 gigabytes RAM. Or on the right hand side, you have some additional hardware, this newer compute stick, for example, that accelerates the running of neural networks on edge devices. So both of these devices show that the resources we nowadays have for IoT tasks may exceed the requirements for the core functionality. This means that we have more devices than we actually use on the device. More resources than we use on the device. So I just printed some exemplary device resource usage on the bottom, where we have a certain part of the hardware or resources reserved for the core functionality, but still have some free and left unused resources, and we want to make use in this scenario of this ambient resources, as we name them in the paper. Still, they are constrained. I mean, even though we have that resources, we have to cope with the constrained resources in the IoT in general, and especially also with heterogeneous devices. So as you can see here, we have lots of different devices. So as I said, having the Pi, the Arduino, and some other devices has to be this P32, and so. Yeah, this is the abstract of the paper, so the red thing should be more or less what I already said. And yeah, throughout the presentation, we will present a placement strategy adapted to the IoT, which will use a traffic base or traffic as main metric for the placement. With this, within the iteration, we're able to show that we can optimize the bandwidth usage and the latency within an IoT network. This is the structure of the talk. So first of all, I will present requirements and objectives that a service placement in the IoT has to meet. Then I will give an overview on related approaches, so service placement solutions from other domains, where we already have some more research. Then we pick one solution from these other domains to adapt it for the IoT. In the algorithm section, I will give more details on what we adapt on this algorithm, and within the evaluation, we first present which metrics are used and the scenarios applied, and after all, or after presenting that, we come to the performance of the algorithm, and afterwards, or at the end, to the conclusion. So requirements and objective. We, in the paper, we defined 7 requirements with certain sub-requirements, so which is listed the main focus of the requirements. So the first is the service requirements. So we have several requirements on hardware, for example, so CPU, memory, storage that's used by a service, or we can also have some network-based requirements, as they have, as services have dependencies to other services, or have certain inter-device communication needed to work. Then we have the continuous placement. So as we are in IoT, we are rather adaptive scenario where we have, for example, also devices leaving or entering the network, or maybe also services that change their behavior, and therefore we have to perform continuous placement. That means that we re-evaluate our placement strategy or placement decision continuous or periodically. Then, as I already showed on the second slide, we have to go with the heterogeneity of devices. So we might have heterogeneous devices in case of, in terms of hardware they or free resources they offer, and as said, also the resource limitation. The main objectives for the placement we put into these 3 years. So the first one would be the service availability, or the availability of the system as a whole, such that it still maintain functionality. The second one is the response latency, so the system should be responsive as a whole. And the third one is the communication overhead shall be reduced, which is especially also in, for example, battery-powered scenarios where we might have wireless communication that costs a lot of energy. So this should be reduced also, for example, to save power or energy. So now we come to related approaches. So this is an excerpt of the approaches we investigated. In the top, I guess we cannot really read them very well. We have the requirements, and we performed, or we applied all of our requirements to the related approaches, and searched for the one that covers most of them, which is in this case, this one here. I will also go more into detail here. So this one already fulfills most of the objective, or already fulfills all objectives. Also allows continuous placement. It includes service dependency. As I said, this was one of the requirements, especially when we have this mesh up to microservices. We will have lots of these dependencies, and it's able to model service requirements such as CPU or RAM usage. Our adaptations to this approach will reduce the communication overhead, and we will introduce an amortization time, and we will use traffic instead of service dependency as optimization tool for this. So the original, or this is the points that we're using the service dependency with the traffic production, and we also had this amortization time. I will cover in the next slide, and yeah, this should be lower than some threshold to avoid unnecessary migrations. So already introduced the amortization time. What is this? Well, the amortization time shall compute the payoff of a migration. So there we have at the top, we set the cost of migration in relation to the benefit. So the cost of migration here would be, for example, the transmission or the transmission of service data, so the code or the state data to the new host where we want to migrate the service, and the payoff here would be the traffic produced before and the traffic produced after. So the benefit in transmitted traffic. So overall, our optimizations here were that we group communication-intensive services. So in the original work, we just had this service dependency, which does not cover how much a service communicates. So there we would have, we would rank a service that's just communicating to another service once a day. We would count it the same as a service that's sending 10 messages per second. And so therefore we grouped out these intensive services to reduce the bandwidth usage, and through the amortization time, we want to, or we avoid unnecessary migrations. This is cost when we migrate the servers to another host, and these are the resource usage of this service. Then we can see here the edges represent service dependencies, and in our case we also have the amount of exchange data there, which is then again important for our metric to reduce the amount of data that's exchanged between devices. Then come to the conclusion. So to the evaluation. So we have different model different scenarios that shall represent typical scenarios, especially for the IoT. First one, we have a linear scenario. Here you can see every service is just dependent from another service. So this is just a chain of requests going on. Then we have a more complex scenario where we have still a part that's linearly, but also have a service here that has multiple dependencies. And after all, we have a bunch of services with multiple dependencies here, which shall more or less reproduce the IoT scenario where we have some control unit accessing data of some kind of sensor or some other entity in the network. So having that said, the scenarios, we come to the environment. We use a Docker or a virtualized environment. We use Docker for emulation of devices, and every device is one Docker container, and we have one device. Here is device 1 that hosts the service placement. So we have exactly the service placement running here on device 1. On software base, it's realized through ESL middleware that was written at our chair, and it allows us to implement the placement itself and so the technology that's needed to place services and to migrate them, as well as to implement the placement strategies. And then at the bottom here we have a store, so this hosts all services that should be placed within the evaluation. So when when device 1 initiates the placement of a service, then a device downloads the service from the store and places it. Then within this environment, we have two configurations. So we have one homogeneous configuration of based on 5 devices with the same resource capabilities, and we have a second environment that's more heterogeneous with a one bigger device and 4 smaller devices. So bigger means that it has more capability in the terms of hardware. So the CPU. Coming to the results, what you can see here is the inter-node traffic, so the traffic between devices. And here we can see that we have especially 4 cases where the TCS, so this is the original algorithm proposed by the related work, has much more traffic than, or produces much more traffic than the CBS, which is the cost-benefit strategy proposed in our paper. Interesting to see is that it's that these high differences are in scenarios with multi-dependent services. So especially in these scenarios, we benefit most from the adaptations we proposed in this paper. Interesting is also these tree scenarios. So this is, just a look here, where we can see only a decrease in internal traffic when we are in the heterogeneous case. The latency itself shows the same behavior. It's not as much as in the internode traffic, but through our adaptation and through the decrease of internode traffic, we were also able to decrease the latency. So what are the implications? So placement algorithms can be adapted to work in the IoT. Even the unoptimized TCS algorithm works within the IoT, but it does not work optimal. And therefore, we can improve the performance, especially for IoT specific or IoT common environments that are quite heterogeneous and have multi-dependent services. And as already said, so latency reduction to traffic decrease was observed. Conclusion, the service placement is a relevant research field in multiple domains. So within the related work analysis, we had a look at the fog environment, the cloud environment, and the network functional virtualization environment. And placements from these domains can be applied within the IoT, but not performing optimal. But still, they can be optimized for the IoT application. And as I said, traffic flow placement metrics improve the latency and bandwidth usage of a typical IoT system. And these heterogeneous environments with multiple service dependencies, which characterize the IoT most, benefit also most from changes. Then come to the next steps. So within the evaluation, we want to introduce new scenarios with more advanced topologies. And within the environments, we want to introduce environments with more devices and also increase heterogeneity in their hardware capabilities. Another point which would be interesting to have a look at is the analysis of machine learning and traffic prediction for placement optimization, and the optimization of the steps of the migration process itself. So the idea there would be to decrease the downtime of services within a migration. Okay, then we have the references, and that would be it. Thanks.
Thank you, Christian. Does anyone have any questions? I've got one. So on your first slide, you had a little graphic of how much CPU memory was used.
Yes.
But then you didn't follow it up later on to say, well, here are our results, how it relates to your introductory point of. So you talked about traffic at the end, but none of the other things.
Okay, yeah, the idea was to introduce the idea of placing microservices within the IoT. So the idea here would be to use these free resources. Later on, we did not evaluate that it should be was more for the motivation.
Okay, that's fine. So that leads me to my next question.
Okay, great.
In your architecture drawing, based on this, you had a placement engine running on one of the nodes.
Yes.
Is there a monitoring system that runs on the other devices that observes the current free resource?
Yes.
Okay.
Yes. There's this middleware running within this network, and that's giving us all we need. So the hardware usage as well as the node traffic and the internode traffic.
Okay. Another question.
Sure.
So you have this service store. Is the placement engine a service, or is it a specially dedicated bit of software? So do you get the placement engine out of the service store? Can it run anywhere, or do you have to explicitly start it on one device?
So it has to be started on one device, but so there are no requirements on which device this has to run. So it was just by chance it was placed on device one. You could also place it on any other device.
Yeah. Okay. Okay. Thank you.
Welcome.
Yes. Your question.
Thank you. Very interesting presentation. Maybe it's a naive question because I don't understand everything, but you show us a function to estimate if it's worth it to replace the this one. This decision is taken given an instant T, or maybe not. It takes in account how long you will be using this service or not, because I will rephrase my question so it's clear. Maybe you have a delta there, it's not so big, but if you're going to run this service forever, it's still worth it to move. I mean, you have to have an account the time you will use the service to see if the amortization will be worth it or not. You have this in account, or?
Yeah, so I mean, how this is done here is, so you have to define a threshold, after which this pays off. Yeah, sorry, maybe I did not emphasize this enough in the talk. You have this threshold, and I mean, this has to be, well, defined meaningful for your case. So there is no definite number that you put there. But so, as you already said, the amortization time itself then calculates after which time this
is worth it to do the exactly. And then this is more if we want to implement this in real scenario. I guess ideally this will be running on a node wireless maybe. Or not. How do you think about, because if we cannot have other services in Node, we will have to download the service to then run it. Have you think about the cost of, maybe we can go to the slides where you have the services?
This one here, or?
With the Docker.
Yeah.
Here, yeah. To download a service store, it's easy because you have a Docker bridge. But if you have a LoRa one, for instance, it's very expensive to download information. But maybe you can have in a okay, this device only have one service 1, 2, 3 and no more, and maybe it gives room to only run these 3 devices. What I'm trying to say is it's not possible always to every device to download every service. Or maybe yes.
Because it's too, okay, I mean, the idea would there be that we have service in the network accessing, for example, the LoRa device.
Okay.
And it might be, or the idea is that it might be beneficial to place a service here such that this device does not have to communicate with another device, so that it can process its data on its own, and therefore you have like less network communication because you can already process data on the device.
Okay. But I was thinking, sorry. We have the device 4, service 1, whatever.
Yeah.
But if tomorrow for the network is better for device 4 to have service B or maybe a new service, for some devices this may be doable, but for others not. But I guess you can include this in your framework to know which device can run which service.
I mean, we also have the service requirement stuff, so
okay.
we check if the device fulfills the requirements of the service.
Okay. I think Thank you.
Any more questions? No? Okay, so let's thank Kristen again. Thank you.
We may look at the agenda now.
Yeah, so that's the end of this session. Now we're going to find the agenda.
Okay.
Posters.
Session 3. Okay. So now it's we have a poster
4
session.
minutes for 4 minutes poster session.
Ah.
Oh, like 14.
What time is it? Yeah, 4 minutes. Yeah.
4 minutes.
14 minutes.
3 minutes. Oh, no,
3 minutes.
That's pretty
But we actually have a free. It's not a hard deadline. The 16:40 unless you have a plane today. But yeah.
Yeah,
If you want to.
So basically the idea is now to discuss a little bit among each other and to go again to the posters and to look at them. And yeah, so with the risk that you will run away afterwards and will not use the opportunity to discuss, yeah, I think we can already speak our closing words. So I don't know if the coordinators want to come up on stage.
Just
now it's just set. Yeah, so as we are running the workshop for the 5th time, as you have seen, it was very good, the attendance rate, so we had a lot of people, so Mauro was working around a little bit, and we were one of the biggest workshops today, so thanks a lot for attending today. Presentations were all very nice. I also liked the schedule that Mauro gave us enough time to do all the action points that we had. The Toilet Madness I also enjoyed a lot. Everybody did a great job. Yeah,
We try to do our best.
Yeah. Yeah, thanks a lot from my side to all the people that handed in a paper. And again, we can tell you that we had lots of submissions this time, and they were all of good quality, so it was really difficult to decide, but in the end we had to decide to stay below, I think we're at 46. And yeah, so that means you were not selected because you were the only papers, but there was a real review process, and you also have seen the reviews. And
We can't hear anything that's going on.
Oh, really? It's better now? Is it better?
Yes, right there.
Perfect. Good. Yeah, and so I just said that the quality of the labels is very good, and also the reviews were very good. So this is also a very important point. So maybe I will jump to that. So.
It's not the right.
Yeah, because this are TBCs, so these are the people that did the reviews, and as you might know, all the work that is done by us and by those people is like more or less leisure time work. So at least those that are in academia don't really have timetables to work at. That means they really agreed to do the work, and we were really satisfied with the reviews also this time. So personally, I can say that the workshop really matured over the past years and reached a very good quality state from the hand-ins, from the reviews, and from the processes. And this, of course, thanks to the people that organized that. Okay, I don't know if you have anything to add.
No.
So I agree with you. I think it was a very good workshop today. And no, I don't have anything else to add. So I'd like to thank everybody for being here, for presenting the paper, also the viewers.
So, support from media. Thank you first to all who put your hard work paper. You put faith on this conference. So congratulations. I hope you get good feedback. feedbacks, which you already include on the review, on the final version. And thank you for you. It's been a pleasure to work together with you. We are working since November, so it's a lot of work behind the curtain, let's say. Okay, now we are concluding, and it's been a pleasure. So now your paper is going to be forever indexed by IEEE. And
yeah, big thank you also to Anna, of course.
Anna, yes.
Join us today here. So yeah, she was at least partly recording for me. Yes.
She couldn't be bothered to drag herself all the way from Canada to here.
Yes. Yes. Okay. Yeah.
So I'd like to thank Martin for coming, giving the keynote.
Oh, yes.
Known him a long time, and it's really interesting talk. So thank you. Yeah.
Yes.
Thanks for the invitation.
Yes. Yes. And it was also perfect. It was really setting the stage for the other talks and really covering very important points. And I would have loved to continue the discussion. Okay, so thanks a lot. I really use the time to discuss a little bit with you. Thank you for the streaming, Shirley. You did a great job.
Thank you, everyone. Have a good day.
Have a good day.
Hannah made some questions, which we didn't really.
Recording stopped.
Okay, you are still there. You can ask.
Yeah. Yeah. Hannah said, I would like to thank the presenter for this work. I am here, Hannah. Two questions, very easy for more. There was 422. So I guess
The question I was asking about how you monitoring to do the placement, because that's what you do. You've got placement in the community.
I'm going to go ahead and close out this room.
Yeah.
If that's okay with everyone.
Sure.
Thank you.
Yeah.
Thank you. I hope you enjoy the rest of your day.
Thank you, you too. Bye.
Okay, we are off.